Have you ever stood outside on a clear night, gazing up at the stars, and felt that sense of wonder wash over you? What you're seeing isn't just a static picture, it's a living, breathing history book written in light. Every single point of light up there is a messenger, and some of those messages have been traveling through the void of space for billions of years to reach your eyes at this very moment. That faint glimmer from a distant galaxy might have begun its journey before our planet even existed, carrying with it secrets from an era lost to time. It's a humbling thought, isn't it, that when we look up, we aren't just looking out into space, we are looking back deep into the past itself. This video is an invitation to unravel that mystery with us. We're going to explore how light acts as a cosmic time capsule, preserving moments from the dawn of the universe and delivering them across unimaginable distances. Think about it. The same light that allows you to read these words is also the key that astronomers use to decode the story of everything, from the violent birth of the universe in the Big Bang to the slow, majestic dance of galaxies taking shape over eons. Light is so much more than just illumination. It's a code, a record, a witness, and by learning to read it, we can piece together the grand narrative of cosmic evolution, understanding not only where we came from but how the universe itself grew and changed. So join us on this journey. Together, we'll follow the path of a photon from its origin in the heart of a star, across millions of light years, through expanding space and shifting time, right down to the lens of a telescope, and ultimately to our own eyes and understanding. By the time we're done, you won't just see the night sky as a beautiful scattering of stars. You'll see it as it truly is, a window into the deepest history of existence, filled with ancient echoes that are still speaking to us if we only know how to listen. But to truly appreciate the messages light brings, we must first understand the messenger itself. Light is far more than just the brightness that fills a room or the glow of a screen. It is a fundamental physical phenomenon, a cosmic courier that has been delivering its parcels of information across the void since the very beginning. Its most astounding feature is its role as a time traveler. Consider the sun, our closest star. The sunlight that warms your skin on a bright afternoon isn't happening in the moment you feel it. It actually left the sun's surface about 8 minutes ago. You are quite literally feeling the past. Now extend that thought outwards. The brilliant star Betelgeuse in the constellation Orion is so far away that its light takes over 600 years to reach us. When you spot it in the winter sky, you are seeing it not as it is tonight, but as it was around the time the Black Death was sweeping through Europe. This incredible journey is possible because of one unshakable rule of the universe. The speed of light in a vacuum is constant. It's the universe's ultimate speed limit, an unwavering 299,792 kilometers per second. Nothing can travel faster. This constancy is what makes light such a reliable witness. It always travels at the same speed, so the time it takes for its information to reach us is a direct and precise measure of distance. A light year, the distance light travels in 1 year, becomes our fundamental cosmic yardstick. This reliability means that when we receive a photon of light from a galaxy 1 billion light years away, we can be absolutely certain it has been on its solitary journey for 1 billion years, carrying a snapshot of that galaxy from 1 billion years in the past. Light itself is a wonderfully strange and dual-natured thing. It behaves both as a wave and as a stream of particles, known as photons. Think of it like this. The wave aspect describes its motion and how it interacts with space, while the particle aspect describes how it delivers its energy, packet by tiny packet. This wave-particle duality is central to how light encodes information. As a wave, light has specific properties, its wavelength, which is the distance between the crests of the wave, and its frequency, which is how many of those crests pass a point every second. These two properties are intimately linked to the energy the light carries. Shorter wavelengths and higher frequencies mean higher energy, like we see in ultraviolet light or X-rays. Longer wavelengths and lower frequencies mean lower energy, like in infrared or radio waves, and it is within these properties that the secrets are locked. The specific mixture of wavelengths emitted or absorbed by an object acts like a unique fingerprint. When astronomers catch the light from a distant star and spread it out into a spectrum, a rainbow of colors, they can see dark lines where specific wavelengths have been absorbed by elements in the star's atmosphere. Each element, like hydrogen, helium, or iron, leaves its own distinct set of lines. By reading this barcode, scientists can determine the star's exact chemical composition. But the information doesn't stop there. The overall color of the light, whether it's more blue or more red, tells us about the object's temperature. A bluish star is incredibly hot, while a reddish star is relatively cooler. Even the motion of an object is revealed through light. If a galaxy is moving away from us, the wavelength of its light gets stretched, shifting its entire spectrum toward the red end, a crucial clue we'll explore later. So every time we point a telescope at the heavens, we are not just collecting light, we are intercepting an ancient data stream, a detailed dispatch that tells us what something is made of, how hot it is, and where it's going. Now, if visible light gives us such a rich story, you might wonder why we need to look at anything else. But our eyes are incredibly limited. They only perceive a tiny sliver of the grand symphony of light that the universe is broadcasting. This full range is known as the electromagnetic spectrum, and it stretches far beyond what we can see. To truly understand the cosmos, we have to listen to all of its channels, from the deep, long bass notes of radio waves to the incredibly high-pitched, energetic screams of gamma rays. Each type of light interacts with matter in a unique way, allowing it to reveal secrets that other wavelengths simply cannot access. It's like trying to diagnose a patient with only one tool. You might get some information, but to get the full picture, you need an entire suite of tests: an X-ray, an ultrasound, a blood panel. Astronomy works the exact same way. Let's start at the long wavelength, low-energy end of the spectrum with radio waves. These are the giants of the cosmic signal, with wavelengths that can be longer than a football field. Because they are so large and lazy, they can slip through vast clouds of interstellar gas and dust that would completely block visible light. This makes them perfect for mapping the cold, dark structures of the universe. Giant radio telescopes like the Very Large Array in New Mexico act as cosmic ears, listening to the faint whispers of cold hydrogen gas, the primary building block of galaxies. They can also detect the telltale signatures of complex molecules drifting in space, the very precursors to life itself. Perhaps most famously, radio astronomy is the field that discovered pulsars, the rapidly spinning corpses of dead stars, and it's the band we use to listen for potential signals from other civilizations. Moving up in energy, we find microwaves. You might know them for heating your leftovers, but their most profound application is in cosmology. The entire universe is faintly glowing with microwave radiation, a cooled-down remnant from the Big Bang itself, known as the cosmic microwave background. This is the oldest light we can observe, a fossilized snapshot of the infant universe when it was just a hot, dense soup of particles. By studying the tiny variations in this microwave glow, astronomers can read the seeds of all future structure, the slight over-densities that would one day gravitationally collapse to form every galaxy, star, and planet we see today. Next comes infrared light, which we often think of as heat. This wavelength is the master of peering through obscuring dust. Invisible light, the bustling center of our own Milky Way galaxy, is completely hidden behind thick cosmic clouds. But switch to an infrared view and the dust becomes almost transparent, revealing a chaotic, star-packed core and the supermassive black hole that resides there. Infrared telescopes like the Spitzer Space Telescope and the James Webb Space Telescope are essential for studying the birth of stars and planets, which often occurs deep within these dusty stellar nurseries. They see the warm glow of protoplanetary disks swirling rings of gas and dust around young stars where new worlds are beginning to form. Then, of course, there's the narrow band we call home, visible light. This is the light our sun emits most powerfully and that our eyes have evolved to see. It reveals the stunning colors and surface details of stars and galaxies, allowing us to classify stars by their temperature: blue for hot, red for cool, and to see the majestic spiral arms of galaxies like Andromeda. By breaking this visible light into a spectrum, we perform chemical fingerprinting, identifying the specific elements present in a star's atmosphere by the unique pattern of dark absorption lines they create. As we climb higher into energy, we reach ultraviolet light. This is the domain of the young and the hot. Massive, newborn stars blaze fiercely in the ultraviolet, and their intense radiation carves out and illuminates vast clouds of gas in spectacular nebulas. UV observations tell us about the most energetic processes in recently formed stellar clusters and help us track the evolution of galaxies by measuring their rates of star formation. It's a light that shows us the cosmic powerhouses, the regions where the universe is actively building its next generation. Further still, we encounter X-rays. If we want to study the most violent and energetic events in the universe, this is our window. Gas heated to millions of degrees by the immense gravity of black holes and neutron stars glows brightly in X-rays. We can use specialized telescopes to image the hot, swirling accretion disk around a black hole or see the shock waves from a supernova explosion slamming into surrounding gas. X-ray astronomy unveils a universe in constant, ferocious upheaval. Finally, at the very highest energy end of the spectrum, we find gamma rays. These are the photons carrying the most punch, born from the most cataclysmic events imaginable: the collisions of neutron stars, the eruptions of black holes, and the deaths of massive stars in hypernovas. NASA's Fermi Gamma Ray Space Telescope monitors the sky for these brilliant, fleeting flashes of gamma ray bursts, some of the most powerful explosions since the Big Bang itself. They represent the absolute extreme limits of physics and energy in our cosmos. No single type of light tells the whole story. A serene-looking galaxy in visible light might be hiding a furious, X-ray, bright black hole at its center. A dark, seemingly empty patch of sky in visible light might be revealed by a radio telescope to be a bustling nursery of cold gas, soon to give birth to new stars. The true power of modern astronomy lies in this multi-wavelength approach. By combining the data from radio dishes, infrared observatories, optical telescopes, and X-ray satellites, scientists can assemble a complete, three-dimensional understanding of an object, its composition, its temperature, its motion, and its history. It is the ultimate toolset for decoding the universe's deepest secrets, allowing us to read every page of the cosmic story, not just the ones printed in black and white. Now, let's take a closer look at one of the most profound consequences of this cosmic data stream, a phenomenon that fundamentally reshaped our understanding of the universe itself. It all begins with a simple, everyday experience: the sound of a siren. You've likely noticed how the pitch of an ambulance siren seems to drop as it races past you. This is the Doppler effect in action. As the vehicle moves toward you, the sound waves are compressed, making the pitch higher. As it moves away, the waves are stretched out, making the pitch lower. Light behaves in a remarkably similar way, but instead of changing pitch, it changes color. When a source of light is moving away from us, the waves of light it emits get stretched out. Since longer wavelengths of light are perceived as more red, this stretching causes the light to shift toward the red end of the spectrum. This is what astronomers call redshift. Conversely, if an object were moving toward us, its light would be compressed, its wavelength shortened, and it would experience a blue shift. Now, in our local galactic neighborhood, we do see some blue shifts. The Great Andromeda Galaxy, for instance, is on a collision course with the Milky Way, and its light is slightly blue shifted, but these are the exceptions. In the grand scheme of the cosmos, when we point our telescopes at galaxies beyond our immediate local group, we see an overwhelming, undeniable trend. Almost everything is redshifted. The light from distant galaxies is systematically stretched, telling us they are all rushing away from us. This discovery is inextricably linked to the work of astronomer Edwin Hubble in the 1920s. By meticulously measuring both the distances to galaxies and their redshifts, he made a startling correlation. He found that the farther away a galaxy was, the greater its redshift, and therefore the faster it was receding from us. This relationship, now known as Hubble's law, was the first direct observational evidence that the universe is not static, but is actively expanding. Think of the universe as a loaf of raisin bread dough that's still rising. As the dough expands, every raisin moves away from every other raisin. From the perspective of any single raisin, all the others are moving away, and the ones farther away are receding faster than the close ones. We are not at some special center of the universe. Any observer on any galaxy would see the same thing, a universe expanding uniformly in all directions. This is where redshift transforms from a simple color change into our most powerful cosmic tool. It acts as both a speedometer and an odometer for the universe. By precisely measuring the redshift of a galaxy's light, we can instantly determine how fast it is moving away from us. And because of Hubble's law, that recessional velocity directly tells us its distance. The greater the redshift, the faster it's moving and the farther away it is. But there's an even more mind-bending implication. Since light takes time to travel, a galaxy that is 1 billion light-years away is also 1 billion years old. We are seeing it as it was 1 billion years in the past, so a high redshift doesn't just mean far away, it means long ago. When astronomers study the light from a galaxy with a tremendous redshift, they are not just looking across space, they are peering back into a much younger, more primitive era of the universe. This stretching of light over cosmic distances is the key that unlocked our modern understanding of cosmology. It provides the foundational evidence for the Big Bang theory, the idea that the universe began in an immensely hot, dense state and has been expanding and cooling ever since. By tracing the redshifts of galaxies back in time, we can mentally rewind this expansion to its logical beginning. Furthermore, the precise details of how this expansion has changed over billions of years, measured by comparing the redshifts of incredibly distant supernova, led to the shocking discovery that the expansion is not slowing down due to gravity as we once thought, but is actually accelerating, a phenomenon driven by the mysterious force we call dark energy. Every photon of redshifted light is a messenger from the past, carrying within its stretched wavelengths the entire history of the universe's growth, from its fiery origin to its unknown future. So if redshift shows us the universe in motion, expanding and evolving over billions of years, you might wonder, how far back can we actually see? Is there a limit? The answer is a resounding yes, and it brings us to the oldest and most profound photograph ever taken, a picture of the universe, not as a collection of galaxies, but as a newborn infant. This picture is the cosmic microwave background, and it is the furthest back in time that any telescope will ever see. It is the leftover heat from the Big Bang itself, a fossilized echo that fills every cubic centimeter of the cosmos. To understand its significance, we need to rewind the cosmic clock. Immediately after the Big Bang, the universe was an unimaginably dense, searingly hot fireball of energy and fundamental particles. It was so hot and dense that light could not travel freely. Electrons were constantly being scattered by photons, creating an opaque, glowing fog. The universe was, for all intents and purposes, a brilliant, blinding plasma. But as the universe expanded, it also cooled. After about 380,000 years, it had cooled enough for a monumental event to occur. Electrons could finally combine with protons to form the first stable hydrogen atoms. This pivotal moment is known as recombination. Suddenly, the fog lifted. With most of the free electrons now locked up in atoms, photons, particles of light, could finally travel unimpeded across the cosmos. That first flash of light, released from the plasma after a journey of 380,000 years, is what we detect today as the cosmic microwave background radiation. It is the literal afterglow of creation. Every direction we point a radio telescope, we see this faint, cold glow. It is the most uniform thing in the universe, but it holds within its subtle imperfections the blueprint for everything we see today. The story of its discovery is a classic tale of scientific serendipity. In 1965, two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, were troubleshooting a persistent problem with a large horn-shaped antenna they planned to use for radio astronomy. No matter where they pointed it, they detected a constant, low-level static hiss that permeated the entire sky. It was there day and night in every season. They scrubbed the antenna clean of what they jokingly called a white dielectric material, which was actually pigeon droppings, but the noise remained. Puzzled and frustrated, they eventually learned that a team of physicists at Princeton, led by Robert Dicke, had been actively searching for precisely this signal, the predicted leftover radiation from a hot, dense beginning to the universe. Penzias and Wilson had accidentally stumbled upon the strongest evidence for the Big Bang, a discovery that would earn them the Nobel Prize. They weren't looking for the genesis of the cosmos. They were just trying to get rid of some annoying static. But their careful work and open-mindedness allowed them to recognize the profound significance of the signal they couldn't eliminate. The initial measurements showed the CMB was remarkably uniform, with a temperature just a few degrees above absolute zero. But the real secrets were hidden in the minutiae. If the early universe had been perfectly smooth, gravity would have had nothing to work with, matter would have been evenly distributed, and galaxies, stars, and planets would never have clumped together. The universe would be a vast, dark, and empty void. So scientists knew there had to be tiny imperfections, minuscule variations in density and temperature imprinted on this cosmic backdrop. Finding them became the next great quest. That quest was triumphantly answered by NASA's Cosmic Background Explorer, or COBE, satellite in 1992. COBE instruments were so sensitive they could detect temperature variations of a mere millionth of a degree, and there they were, the seeds of all structure. The COBE map revealed the ancient universe was not perfectly smooth. It was a mottled canvas of slightly warmer and slightly cooler patches. These tiny ripples represented regions of space that were ever so slightly denser or less dense than average. These fluctuations are the single most important discovery in modern cosmology. They are the gravitational seeds from which the entire cosmic web grew. Over hundreds of millions of years, gravity acted on these slight over-densities. The tiny bit of extra gravity in a slightly denser region would pull in more matter from its surroundings, making it even denser. This runaway process eventually sculpted those primordial ripples into the first stars, the first galaxies, and the vast filamentary structures that connect them across the void. The pattern of these fluctuations is like a cosmic fingerprint, encoding fundamental information about the composition and geometry of the universe. By studying their size and distribution with even greater precision using later missions like the Wilkinson Microwave Anisotropy Probe and the Planck satellite, cosmologists have been able to determine the universe's age with incredible accuracy, 13.8 billion years, and its precise recipe, about 5% ordinary matter, 27% dark matter, and 68% dark energy. The cosmic microwave background is therefore much more than a static photograph. It is a dynamic data stream from the dawn of time. It is our most direct link to the universe's moment of birth, a baby picture that confirms our deepest theories about cosmic origins and provides the initial conditions for the entire story of evolution that followed. It is the ultimate validation that we live in a universe with a definite beginning, one that has been expanding and cooling ever since, and one whose fate is written in the faint, cold whisper of microwaves that surround us all. So we've seen how light can be stretched by the expansion of the universe, but how do we actually pull specific, detailed information from that distant starlight? How do we move from simply seeing that a galaxy is far away to knowing what it's made of, how hot it is, or how quickly it's spinning? The answer lies in one of the most powerful tools in all of science, a technique that transforms a simple beam of light into a detailed cosmic biography. This tool is called spectroscopy, and it allows us to read the unique fingerprints that elements leave on light. Think of it like this. If you were a detective investigating a crime scene, you wouldn't just take a photograph of the room and call it a day. You'd dust for fingerprints, analyze fibers, and test for chemical residues. Each piece of evidence tells a specific part of the story. In astronomy, light is our crime scene, and spectroscopy is our forensic kit. It lets us move beyond the pretty pictures and start to understand the very substance of the cosmos. The fundamental principle behind this is surprisingly simple and was discovered right here on Earth centuries before we could apply it to the stars. It begins with one of the most beautiful phenomena in nature, the rainbow. When sunlight passes through water droplets in the air, it spreads out into its constituent colors. In the 1600s, Isaac Newton famously used a glass prism to demonstrate that what we perceive as white light is actually a mixture of all the colors of the rainbow, which he called a spectrum. But it was in the early 1800s that the real breakthrough happened. A German physicist named Joseph von Fraunhofer was perfecting the manufacture of optical glass when he noticed something peculiar. When he looked very closely at the sun's spectrum, it wasn't a perfect, continuous rainbow. It was scarred by hundreds of fine, dark lines like tiny barcodes etched into the light. He meticulously mapped these lines, though he had no idea what caused them. We now call them Fraunhofer lines, and they are the key to everything. We now understand that these lines are created by the elements themselves. Here's how it works. Every element in the universe, hydrogen, helium, iron, oxygen, you name it, has a unique atomic structure. This structure dictates how it interacts with light. When an electron inside an atom absorbs a specific, precise amount of energy, it can jump to a higher energy level. Conversely, when it falls back down, it releases that same specific amount of energy in the form of a photon of light. The amount of energy involved is unique to each element, which means the color or wavelength of the light absorbed or emitted is also unique. It's a fundamental atomic signature. It's as if every element has its own musical note that it can either sing or listen for. This gives us two primary types of spectral lines that tell our story. First, there are emission lines. Imagine a hot, thin cloud of gas, like a neon sign or a glowing nebula in space. The atoms in that gas are excited and emitting light at their specific, characteristic wavelengths. When we pass that light through a spectroscope, a modern version of Fraunhofer's prism, we see a pattern of bright, colored lines on a dark background. This pattern is a direct fingerprint, a set of lines in the red, blue, green, and violet, that's hydrogen, a specific set of yellow lines, that's sodium. It's a direct broadcast of the cloud's chemical composition. The second type, and the one Fraunhofer saw in the Sun, are absorption lines. Now imagine a hot, dense object like a star that produces a continuous spectrum of light, a perfect rainbow. But between that light source and us, there is a cooler, thinner atmosphere of gas. As the light from the dense core passes through this cooler gas, the atoms in that atmosphere absorb the very specific wavelengths of light that they prefer, the ones that match their own unique energy transitions. When we analyze the resulting spectrum, we see a continuous rainbow but with specific, sharp dark lines missing, exactly at the wavelengths those atoms absorbed. It's like a thief has stolen specific colors of light, and the missing pieces, the gaps in the rainbow, tell us exactly which elements are present in the star's outer atmosphere, acting as a light filter. But the story doesn't end with a simple ingredient list. This fingerprint can tell us so much more. The width and depth of the spectral lines are like the fine print on a contract, revealing additional details. Broader lines can indicate a higher density of gas or the presence of strong magnetic fields twisting the atoms. The precise position of a set of lines can reveal an object's motion through the Doppler effect we discussed earlier, showing whether it's moving toward us or away from us. Even the temperature of a star can be gauged by which elements are showing the strongest lines. Cooler stars might show strong lines for molecules like titanium oxide, while extremely hot stars will show lines for ionized helium. This technique is what allows us to say with absolute certainty that the same hydrogen and helium that make up our Sun are found in galaxies billions of light years away. It's how we know that the universe is chemically uniform, operating under the same physical laws everywhere we look. By decoding the subtle shifts in these fingerprints, we can measure the spin of distant galaxies, detect the powerful magnetic fields around neutron stars, and even identify the complex, organic molecules drifting in the vast clouds between the stars, the very building blocks of life itself, all revealed by the missing colors in a beam of ancient light. Spectroscopy is the true language of the cosmos, and we have learned to read it. Just as a towering oak tree begins as a tiny seed, every star, including our own Sun, has a humble origin story written in light and gas. It all starts within the cold, dark, and seemingly empty vastness of a nebula, a cosmic cloud of gas and dust, often the scattered remains of a long-dead star. Within these stellar nurseries, gravity begins its slow, patient work, pulling together pockets of hydrogen and helium. As this material condenses, it forms a protostar, a nascent sun still shrouded in its dusty cocoon. To our eyes, these regions might look like dark voids, but switch to an infrared telescope, and the story changes completely. The dust that blocks visible light glows warmly in the infrared, revealing the hidden, collapsing cores where new stars are igniting. The light from this stage is not from nuclear fusion yet, but from the immense gravitational energy released as the star baby squeezes itself tighter and tighter, growing hotter with every passing millennia. The moment of true stellar birth arrives when the core of the protostar becomes so incredibly hot and dense that it triggers the universe's most fundamental power source, nuclear fusion. Hydrogen atoms are forced together under immense pressure to form helium, releasing a staggering amount of energy in the process. This energy, rushing outward from the core, creates a pressure that perfectly balances the inward crush of gravity. The star achieves stability and begins what is known as its main sequence life, the longest and most stable phase of its existence. Our Sun has been in this hydrogen-burning stage for about 4.5 billion years and has another 5 billion or so to go. During this long adulthood, a star's light acts as a steady beacon. Its color, which is directly tied to its surface temperature, tells us its mass and age. Massive, powerful stars burn ferociously hot and fast, shining with a brilliant blue-white light. Smaller, more frugal stars, like our Sun, glow a steady yellow, while the smallest, coolest stars emit a dim, red light and can live for trillions of years. But like all lives, a star's main sequence phase cannot last forever. The fuel in its core will eventually run low. For a star like our Sun, the end of its hydrogen supply initiates a dramatic and beautiful transformation. With the energy from fusion waning, gravity begins to win the battle again. The core contracts and heats up even further, while the outer layers expand outward, cooling as they go. The star swells into a red giant, its diameter ballooning to engulf the inner planets. During this phase, the star's light tells a clear tale of its changing structure. The expanded, cooler surface shifts its color dramatically toward the red end of the spectrum, making it one of the brightest red objects in the galaxy. Meanwhile, in the intensely hot core, a new chapter begins as helium atoms begin to fuse into carbon and oxygen. This is the beginning of the end, but also the start of a star's most crucial contribution to the cosmos. The final fate of a star is a story written entirely in its mass, and its light is the final message it sends. For low to medium mass stars like our Sun, the red giant phase ends not with a bang, but with a whisper. The star gently shrugs off its outer layers, creating a breathtakingly beautiful planetary nebula, a glowing shell of ionized gas that expands into space. For a few tens of thousands of years, this nebula shines with the specific emission lines of the elements forged within the star: hydrogen, helium, carbon, and oxygen. At the heart of this glowing cloud, all that remains is the star's incredibly dense, hot core, now exposed as a white dwarf. No longer generating energy through fusion, a white dwarf simply cools over billions of years, fading from white to yellow, to eventually a cold black dwarf, a dark cinder in space. Its light tells a story of gradual cooling and final stillness. For stars many times more massive than our Sun, the finale is far more spectacular and violent. Their immense gravity allows them to forge elements far heavier than carbon and oxygen, creating a layered onion-like structure with iron accumulating at the core. But iron is a cosmic dead end. It absorbs energy to fuse rather than releasing it. When the iron core grows too large, the support against gravity vanishes catastrophically. The core collapses in less than a second, triggering a titanic rebound explosion known as a supernova. For a brief moment, a single supernova can outshine an entire galaxy, emitting light across the entire electromagnetic spectrum. The intense energy of the blast fuses elements heavier than iron, the gold in your jewelry, the uranium in power plants, the silver in photographic film, and flings them out into the universe at tremendous speeds. The light from a supernova carries the unmistakable fingerprints of these newly created heavy elements, seeding the cosmos with the raw materials for rocky planets and ultimately life itself. What remains after the supernova blast is just as telling. The collapse of the core can leave behind one of two incredibly dense objects. If the core is between about 1.4 and 3 solar masses, it collapses into a neutron star, a city-sized object so dense that a single sugar cube-sized piece of it would weigh as much as a mountain. Neutron stars often spin rapidly, and if they have strong magnetic fields, they can beam out pulses of light like a cosmic lighthouse. These pulsars are identified by their incredibly regular, pulsing light, a dead giveaway of their nature. For the most massive stars, the core collapse is so complete that not even neutrons can support it. The gravity is so strong that it warps space-time itself, creating a region from which not even light can escape, a black hole. While the black hole itself emits no light, its presence is betrayed by the behavior of light and matter around it. We detect the intense X-rays emitted by superheated gas as it is ripped apart and spirals into the event horizon, a final, violent signature of a star that lived fast, died young, and left a mysterious corpse. This incredible life cycle is not just a historical record. It's a process we can observe happening all around us in real time, thanks to the time-traveling nature of light. In one region of a nebula, we might use infrared telescopes to see new stars being born. In another part of the sky, we can study the steady yellow light of main sequence stars like our Sun. By looking farther out into the universe, and thus farther back in time, we can observe the red giants and supernova of stars that lived and died long before our Sun was even a twinkle in a nebula's eye. This ability to see all stages of stellar life simultaneously allows astronomers to assemble the complete narrative from cradle to grave. The light from stars is their autobiography, a detailed chronicle of their mass, age, composition, and ultimate fate, telling us not only how they lived and died, but how their deaths made our own existence possible. But stars are rarely solitary actors in the cosmic drama. They congregate by the billions into the grandest structures of all galaxies. These immense islands of stars, gas, and dust are the fundamental building blocks of the visible universe, and their collective light offers us something even more profound than the story of a single star, a complete chronological record of cosmic evolution. When we observe a galaxy, we are not just seeing a random splatter of stars. We are looking at a dynamic system with a history, and its light is the archive where that history is stored. Every characteristic of that light, its color, its intensity, its spectrum holds a clue. The overall shape of a galaxy, whether it's a majestic spiral with graceful arms, a smooth and featureless elliptical, or an irregular blob, tells us about its past interactions. A serene, round elliptical galaxy might be the ancient, quiet remnant of a violent merger between two spirals billions of years ago, its gas used up in a furious burst of past star formation. A delicate spiral, by contrast, suggests a more peaceful history with its orderly rotation and ongoing star birth in its dusty arms. This is where the time-traveling magic of light becomes our most powerful tool. Because light takes time to reach us, a telescope is not just a window into space, but a portal into the past. When astronomers point their most powerful instruments at a galaxy 1 billion light-years away, they are seeing it as it was 1 billion years ago. By looking at a galaxy 2 billion light-years away, they peer 2 billion years into the past. This allows for an incredible scientific shortcut. We don't have to wait billions of years to watch a single galaxy evolve. Instead, we can simply look out to greater and greater distances to see galaxies at progressively younger and younger stages of their lives. It's like walking through a forest and being able to see seedlings, saplings, mature trees, and fallen logs all at once. By comparing them, you can reconstruct the entire life cycle of a tree without having to wait a century. This comparative approach reveals a dramatic story of change. The most distant, and therefore youngest, galaxies we can observe are profoundly different from our own Milky Way. They often appear smaller, clumpier, and more irregular. Their light is frequently bluer in color, a telltale sign of intense and frantic star formation. These infant galaxies are busy forging their first generations of stars, burning hot and bright with the raw, abundant fuel of primordial gas. They are also more chaotic, frequently colliding and merging with their neighbors in a violent cosmic dance that helps them grow. As we look at galaxies closer to us, and therefore closer to the present day, we see the results of this evolution. Through a series of mergers and the steady consumption of gas, galaxies grow larger, and their gravitational pull shapes them into more defined forms like spirals and ellipticals. The frenetic pace of star formation slows down. The massive, hot blue stars that live fast and die young burn out first, leaving behind the longer-lived, cooler, redder stars. This gradual change in stellar population causes the galaxy's overall color to shift from blue to yellow to red over billions of years, a process astronomers call cosmic downsizing. The light from a galaxy allows us to measure this evolution with stunning precision. By analyzing its spectrum, we can determine not just its composition, but its star formation rate essentially, how many new stars it is giving birth to each year. A galaxy with strong emission lines from hydrogen gas is likely a stellar nursery, alive with newborn stars. A galaxy whose spectrum is dominated by the absorption lines of older, cooler stars is a quiet, aging system. We can even measure how fast a galaxy is rotating by looking for the Doppler shift in its light. One side of a spinning spiral galaxy will be slightly blue-shifted as it moves toward us, while the other side is red-shifted as it moves away. This rotation speed, combined with the galaxy's observed size, allows us to calculate its mass, including the vast, invisible halo of dark matter that holds it all together. This grand narrative of galactic evolution isn't just about individual islands. It's about the architecture of the universe itself. Galaxies are not scattered randomly through the void. Instead, they form an immense cosmic web, a vast network of filaments and clusters surrounding enormous voids. This large-scale structure is the result of gravity acting over billions of years on the tiny density fluctuations we see in the cosmic microwave background. The light from millions of galaxies, meticulously mapped in surveys like the Sloan Digital Sky Survey, allows us to trace this web in 3 dimensions. By measuring their redshifts, we can plot their positions in space and time, revealing the grand design of the cosmos. This structure shows us that galaxies are the visible traces of an underlying skeleton made mostly of dark matter, and their distribution confirms our deepest theories about the origin and evolution of everything. Each galaxy, from the brightest giant to the faintest dwarf, is a data point in the universe's biography, and their light is the ink with which that story is written. So we've mapped the grand tapestry of galaxies, but this visible universe, this breathtaking cosmic web of stars and nebulae, is merely the tip of the iceberg. In fact, it's a very small tip. The stars, planets, gas, and dust, everything we can see and touch, and are made of account for a mere 5% of the total content of the universe. The remaining 95% is invisible, undetectable by any telescope operating in any wavelength of light. This is the realm of the dark universe, dominated by 2 of the most profound and puzzling discoveries in all of science: dark matter and dark energy. They are utterly mysterious, yet their influence is everywhere, and we know they exist for one simple reason: they leave their fingerprints all over the light we can see. Let's start with dark matter. The story of its discovery begins not in the depths of space, but with the careful observation of how galaxies move. In the 1930s, a brilliant and meticulous astronomer named Vera Rubin was studying the rotation of spiral galaxies. By measuring the Doppler shift of light from stars and gas clouds at different distances from a galaxy's center, she could plot how fast those stars were orbiting. According to the laws of gravity established by Newton and refined by Einstein, stars on the outer edges of a galaxy, where visible matter is more sparse, should be moving much more slowly than those near the bright, dense center. Think of our solar system. Pluto, far out on the edge, orbits the Sun much more slowly than Mercury, which is close in. But what Rubin found was astonishing. The stars at the outer edges of galaxies were orbiting just as fast as those near the center. The entire galaxy was rotating as if it were a single, solid disk. This made no sense. There simply wasn't enough visible mass in the galaxy to generate the gravity required to hold these swiftly moving outer stars in their orbits. They should have been flung off into intergalactic space. The only possible explanation was that there had to be a tremendous amount of additional mass that we couldn't see, mass that was providing the extra gravitational glue. This invisible material was dubbed dark matter, but if we can't see it, how do we know it's really there? This is where light becomes our detective. While dark matter doesn't emit, absorb, or reflect any light, it does have mass, and therefore it has gravity. And gravity, as Einstein taught us, can bend the very fabric of space-time itself. This means it can also bend the path of light traveling through it. This phenomenon is called gravitational lensing, and it is one of the most powerful tools we have for mapping the invisible. Imagine a massive object like a cluster of galaxies sitting between us and a more distant galaxy. The immense gravity of the cluster, mostly provided by its halo of dark matter, warps the space around it, acting like a giant cosmic lens. When light from the background galaxy passes through this warped space, its path is bent. From our perspective, the image of that distant galaxy can be distorted into spectacular arcs and rings, known as Einstein rings. By meticulously studying the precise way these background images are stretched and twisted, astronomers can create a detailed map of the mass responsible for the lensing effect. And time and again, these maps reveal that the vast majority of the mass is not where the visible galaxies are, but spread out in a huge, smooth, invisible halo. We are literally seeing the shadow of dark matter by watching how it manipulates the light from objects behind it. Now, if dark matter is the invisible scaffolding that holds galaxies and clusters together, dark energy is the mysterious force that is pulling the entire universe apart at an ever-increasing rate. Its story also comes from carefully reading the light of distant objects, specifically a special kind of stellar explosion. In the late 1990s, two independent teams of astronomers were using Type Ia supernova as cosmic distance markers. These supernova are incredibly useful because they all explode with nearly the same intrinsic brightness. Think of them as standard light bulbs. If you know how bright a light bulb truly is, you can calculate how far away it is by how dim it appears to you. The teams were measuring these supernova in extremely distant galaxies to see how the expansion rate of the universe had changed over time. Everyone expected that the gravity of all the matter in the universe would be acting as a brake, causing the expansion to slow down. But the data revealed the exact opposite. The distant supernova were significantly dimmer than they should have been if the expansion were slowing. The only explanation was that these supernova were farther away than previously thought, meaning the universe hasn't just been expanding. Its expansion has been speeding up for the last several billion years. Some repulsive force counteracting gravity was pushing galaxies apart faster and faster. This force was named dark energy. The light from those ancient supernovae delivered a shocking message. The universe is not only dominated by stuff we can't see, but its ultimate fate is being driven by an anti-gravity force we don't understand. Combined with other evidence, like the patterns in the cosmic microwave background, we now know that dark energy makes up about 68% of the universe, while dark matter makes up about 27%, leaving our familiar world of atoms and light as a mere 5% afterthought. Dark matter's gravity builds the structures, while dark energy's push threatens to tear them apart over unimaginable timescales. They are the yin and yang of the cosmos, the two great invisible forces engaged in a cosmic tug of war with the fate of everything hanging in the balance. And we only know any of this because we have learned to read the subtle ways they interact with the one thing they cannot completely hide: light. While the quiet fade of a white dwarf is one stellar ending, the universe reserves its most spectacular finales for its most massive stars. These are the supernova, cosmic explosions of such unimaginable power that for a few glorious weeks, a single star can outshine the combined light of every other star in its entire galaxy. It is the ultimate stellar death, but also a magnificent rebirth, a violent and beautiful event that seeds the cosmos with the very elements that make life possible. The light from a supernova is not just a flash in the dark. It is a complex and information-rich signal, a cosmic broadcast that tells us about the star's life, its death, and the fundamental nature of the universe itself. To understand the sheer scale of this event, consider the physics at play. In the core of a truly massive star, nuclear fusion is a race against time. The star spends its life fusing progressively heavier elements, hydrogen into helium, helium into carbon, and so on, building up layers like a cosmic onion. This process continues until the core is primarily iron, but iron is different. Fusing iron atoms doesn't release energy, it consumes it. Suddenly, the star's central engine sputters and dies. With no outward pressure from fusion to counter it, the immense force of gravity wins in an instant. The core collapses at nearly a quarter the speed of light, cramming a mass greater than our Sun into a sphere just a few dozen kilometers across. The collapse halts so abruptly that it sends a devastating shockwave racing back out through the star's outer layers. This rebounding shock, combined with a torrent of neutrinos pouring from the core, literally blows the star apart from the inside out. The energy released is beyond human comprehension. In a single second, a supernova can emit more energy than our Sun will in its entire 10 billion-year lifetime. This cataclysm floods space with light across the entire electromagnetic spectrum, creating a signature pattern of brightening and fading known as a light curve. For astronomers, this light curve is a treasure trove of data. The way the supernova's brightness rises to a peak and then gradually declines tells a detailed story about the explosion's mechanics, the composition of the ejected material, and even the amount of radioactive elements like nickel-56 forged in the blast which decay and power the long-term fading of the light. But perhaps the most crucial application of this light is as a cosmic measuring tape. This is where a specific type of supernova called Type Ia becomes the hero of the story. Type Ia supernova are thought to originate in binary star systems where a white dwarf, the dense remnant of a sun-like star, is siphoning material from its companion. When the white dwarf greedily accumulates enough mass to reach a critical threshold, about 1.4 times the mass of our Sun, it triggers a runaway thermonuclear explosion that completely obliterates the dwarf. Because this critical mass is always the same, the resulting explosion always has approximately the same intrinsic brightness. This makes Type Ia supernova what astronomers call standard candles. If you know how bright something truly is, you can calculate its distance by measuring how dim it appears. It's like knowing the wattage of a light bulb. If you see it looking faint, you know it must be far away. It was by meticulously observing the light from these incredibly distant standard candles that two teams of astronomers made a discovery in the late 1990s that turned cosmology on its head. They were measuring Type Ia supernova in galaxies billions of light-years away, expecting to confirm that the expansion of the universe was slowing down due to the gravitational pull of all matter. But the light told a different story. The supernova were significantly dimmer than expected. This meant they were farther away than their redshifts indicated they should be. The only possible explanation was that the expansion of the universe wasn't slowing down at all. It was speeding up. Some mysterious repulsive force, counteracting gravity, was pushing galaxies apart faster and faster. This force was dubbed dark energy, and the Nobel Prize-winning discovery was made possible by reading the light from these dying stars. Beyond measuring distances and revealing dark energy, the light from a supernova also carries the chemical fingerprints of the elements created in the explosion. The ferocious energy of a supernova is the only environment in the universe violent enough to forge elements heavier than iron, like gold, silver, platinum, and uranium. As the expanding shockwave plows into the surrounding interstellar medium, it heats the ejected material to incredible temperatures, causing it to glow brilliantly. When astronomers spread this light out into a spectrum, they can see the bright emission lines of these newly synthesized elements. Every time we observe a supernova, we are witnessing the cosmic alchemy that enriches the galaxy with the raw materials for rocky planets and ultimately for life. The iron in your blood, the calcium in your bones, and the oxygen you breathe were all forged in the heart of a long-dead star and scattered across the galaxy by a supernova explosion billions of years ago. We are quite literally made of stardust, and supernova are the delivery mechanism. These brilliant, fleeting beacons are therefore far more than just spectacular fireworks. They are fundamental probes of cosmic distances, the discoverers of dark energy, and the universe's primary chemists, responsible for creating and distributing the elements of life. The light from a single supernova, observed for a few months, can tell us more about the structure, history, and fate of the cosmos than the steady light from a billion normal stars observed for a century. They are the universe's most powerful and informative explosions, brief flashes in the dark that illuminate the deepest secrets of existence. If supernova are the universe's most powerful explosions, then quasars are its most powerful engines, shining with a ferocious brilliance that defies belief. Discovered in the early 1960s, these objects looked like faint blue stars in visible light telescopes, earning them the name quasi-stellar radio sources, or quasars for short. But their true nature was revealed not by how they looked, but by their incredible redshifts. These seemingly stellar pinpricks of light were not stars in our own galaxy at all. They were fleeing from the edge of the observable universe, billions of light-years away. For an object at that distance to be visible at all, it had to be emitting almost unimaginable amounts of energy. A single quasar can outshine 1,000 galaxies, each containing hundreds of billions of stars, all from a region not much larger than our solar system. The question was, what natural engine could possibly generate that much power? The answer lies in the most efficient energy conversion process in the universe: gravity. At the heart of every quasar lies a supermassive black hole, a gravitational monster with a mass millions or even billions of times that of our Sun. But a black hole alone is just a dark pit in space. It's the material falling into it that creates the spectacle. Imagine a vast whirlpool of gas, dust, and even entire stars forming a swirling, superheated disk around the black hole, known as an accretion disk. As this material spirals inward, it is compressed and heated to temperatures of millions of degrees, causing it to glow intensely across the entire electromagnetic spectrum, from X-rays to radio waves. Friction within the disk and powerful magnetic fields can also launch twin jets of particles at nearly the speed of light, shooting out from the poles of the black hole and extending for hundreds of thousands of light years into intergalactic space. It is this entire system, the black hole, the accretion disk, and the jets that we call an active galactic nucleus, with quasars being the most luminous and distant examples. Because they are so incredibly bright, quasars act as the ultimate cosmic lighthouses. Their light can be seen from the farthest reaches of space and time, making them perfect probes for studying the early universe. The most distant quasars we have observed are seen as they were when the universe was less than 1 billion years old, a mere 7% of its current age. Their very existence at such an early epoch is a fascinating puzzle for astronomers, telling us that supermassive black holes were able to form and grow to immense sizes very quickly after the Big Bang. The light from these ancient beacons has been traveling for over 13 billion years to reach us, carrying with it a pristine record of the conditions in the infant cosmos. As this brilliant light makes its multi-billion-year journey to Earth, it doesn't travel through empty space. It passes through the vast, diffuse clouds of gas that float in the voids between galaxies, a sparse and mostly invisible medium known as the intergalactic medium. This is where the quasar's light performs its most valuable trick. When the light spectrum is analyzed, astronomers don't just see the bright emission lines from the hot gas in the quasar's accretion disk. They also see a forest of dark absorption lines, hundreds or even thousands of fine lines sliced into the spectrum. Each one of these lines is a fingerprint, a specific wavelength of light that was absorbed by a cloud of neutral hydrogen gas along the line of sight. Because the universe is expanding, each cloud is at a slightly different distance and thus has a slightly different redshift. This creates a dense thicket of lines known as the Lyman alpha forest that represents a complete history of the gas the light encountered on its journey. By decoding this forest, astronomers can do something remarkable. They can map the cosmic web. They can determine the density, temperature, and chemical composition of the invisible gas that constitutes the vast majority of the normal matter in the universe. This analysis reveals how this primordial gas has been enriched over time with heavy elements blown out by generations of supernova, and how it has been sculpted by the gravity of dark matter into the filamentary structure that defines the large-scale architecture of the cosmos. A quasar's light acts like a flashlight beam shone through a cosmic fog, and the shadows it casts allow us to chart the geography of that fog. Without these distant, brilliant beacons, the intergalactic medium would remain almost entirely hidden from our view. Furthermore, the study of quasars has profoundly shaped our understanding of galaxy evolution. It appears that nearly every large galaxy, including our own Milky Way, harbors a supermassive black hole at its center. But not all are active. Ours is currently dormant, a sleeping giant. This suggests that the quasar phase is a temporary, albeit dramatic, period in a galaxy's life, likely triggered by a major influx of gas, perhaps from a collision with another galaxy. The energy unleashed by a quasar is so tremendous that it can drive powerful winds that blow away the surrounding gas, effectively shutting off the fuel supply for both future black hole growth and for the formation of new stars in the galaxy. This process, called feedback, may be the key reason why we don't see galaxies growing indefinitely larger. the quasar, in its brilliant death throes, might actually be responsible for its own demise and for regulating the growth of its host galaxy. These distant beacons are not just passive signposts, they are active and violent participants in the story of cosmic evolution, their light narrating a tale of incredible power, growth, and ultimate self-destruction that shaped the universe we see today. But perhaps the most incredible application of gravitational lensing is its ability to act as a natural, cosmic-scale telescope, dramatically magnifying the most distant objects in the universe. This effect, called strong lensing, is what creates those stunning Einstein rings and luminous arcs we sometimes see in Hubble images. When the alignment between a massive foreground cluster and a background galaxy is nearly perfect, the gravity of the cluster bends the light from the more distant object around it, warping its image into a complete or partial circle of light. These rings are not just beautiful cosmic oddities, they are incredibly precise tools. The exact shape and brightness of the ring depend directly on the mass of the foreground object, allowing astronomers to make exquisitely accurate measurements of that mass. Even more remarkably, this natural magnification allows us to see galaxies that would otherwise be far too faint and small to detect. The light from these incredibly distant objects is amplified, giving us a detailed look at galaxies in the very early universe, revealing their structure, their rate of star formation, and even the properties of individual star-forming regions within them. It's as if the universe itself has provided us with a giant magnifying glass to study its own infancy. Beyond these dramatic rings and arcs, there is a far more subtle and widespread form of lensing at work, one that affects the entire sky. This is known as weak gravitational lensing. Instead of creating bold, easily visible distortions, the gravity of every galaxy, cluster, and filament of dark matter ever so slightly shears the images of the billions of background galaxies behind them. The effect on any single galaxy is minuscule, virtually imperceptible, but by employing powerful statistical analysis on vast surveys of the sky, containing millions of galaxies, astronomers can detect a consistent, coherent pattern of tiny distortions. It's like looking at a landscape through a slightly wavy pane of glass. You might not notice the distortion on any single object, but by analyzing the entire view, you can map the exact imperfections in the glass. This technique allows cosmologists to create enormous three-dimensional maps of the dark matter distribution throughout the universe. These maps confirm that dark matter forms an intricate cosmic web, a scaffolding of filaments and nodes upon which visible galaxies are built like glitter on a dark thread. Weak lensing is our primary tool for weighing this invisible skeleton of the cosmos and understanding how its structure has evolved over billions of years. There is even a third, incredibly precise category known as microlensing. This occurs when a single, compact object like a star, a planet, or even a black hole passes directly in front of a more distant star. The gravity of the foreground object acts as a tiny lens, briefly focusing the light of the background star and causing it to momentarily brighten. The duration and shape of this brightening event are like a signature, telling astronomers about the mass of the object causing the lensing, even if that object emits no light whatsoever. This technique has become a powerful method for discovering objects that would otherwise be completely invisible to us, such as isolated black holes drifting through the galaxy or planets that roam freely in the dark between stars, untethered to any sun. Each tiny flash of light is a clue, revealing the presence of the unseen and helping us take a census of the dark, compact objects that populate the Milky Way. Gravitational lensing is a phenomenon that beautifully marries the elegant predictions of Einstein's theory with profound practical discovery. It transforms gravity from just a force that pulls on matter into an active component of our observational toolkit, a cosmic curator that bends and shapes light to reveal the universe's deepest secrets. From mapping the invisible dark matter that holds galaxies together to magnifying the faintest glimmers from the cosmic dawn, this remarkable effect demonstrates that sometimes, to see the universe more clearly, we must first learn to appreciate its twists and turns. For all its theoretical power, a telescope is only as good as the clarity of its view, and for centuries, Earth's atmosphere was the ultimate obstacle. Our protective blanket of air, which makes life possible, is a constant, shimmering barrier to clear sight. It distorts starlight, blurs fine details, and blocks entire wavelengths of light from ever reaching the ground. Astronomers dreamed of a solution, an observatory above the atmosphere, a silent sentinel orbiting in the pristine blackness of space. That dream was realized on April 24, 1990, when the Space Shuttle Discovery carried the Hubble Space Telescope into low Earth orbit. Its journey, however, began with a moment of heart-stopping panic. Shortly after deployment, engineers discovered a catastrophic flaw in its primary mirror. Though polished to near perfection, the mirror was ground to the wrong shape, off by a mere 1/50th the width of a human hair. This tiny error was enough to render Hubble's vision hopelessly blurry, a crushing disappointment after decades of planning and a $2 billion investment. For 3 years, Hubble became a symbol of failure, a punchline on late-night television. But then, in a stunning display of human ingenuity and courage, a rescue mission was launched. In December 1993, astronauts aboard the Space Shuttle Endeavour performed a series of unprecedented spacewalks, installing a set of corrective optics, essentially a complex set of glasses, that restored the telescope's sight. It was one of the most dramatic repair jobs in history, transforming Hubble from a cosmic embarrassment into the most celebrated scientific instrument ever built. Freed from the atmosphere's turbulent veil, Hubble's crystal-clear vision opened new windows on the universe. Its position high above Earth allows it to observe across the ultraviolet, visible, and near-infrared spectrum with a clarity and consistency impossible from any mountaintop. This freedom from atmospheric distortion gives its images an almost magical sharpness, revealing details in celestial objects that were previously just fuzzy blobs. But Hubble is far more than a spectacular camera. It is a time machine. Its ability to peer into the deep universe with such precision means it is collecting light that has been traveling for billions of years. Every image it takes is a snapshot of the past, and its most profound revelations have come from staring for days at what seemed to be nothing. In 1995, astronomers pointed Hubble at a tiny, dark patch of sky in the constellation Ursa Major, an area equivalent to about 1/10 the size of the full moon as seen from Earth. For 10 consecutive days, the telescope gathered every precious photon that fell upon its mirror. The resulting image, known as the Hubble Deep Field, was nothing short of revolutionary. That seemingly empty piece of sky was in fact teeming with light. It contained over 3,000 galaxies, each a sprawling island of stars, each at a different distance and thus a different time in cosmic history. Some appeared as mature spirals, while others were small, bluish, and irregular, the building blocks of the giant galaxies we see today. This single image provided humanity's first clear look at the youthful universe, proving that galaxies were plentiful and already forming when the cosmos was very young. It was a census of creation, a core sample drilled deep into space and time, revealing the universe to be far more vast and richly populated than we had ever imagined. Hubble's contributions extend far beyond this iconic deep field view. It has been the premier tool for pinning down the Hubble constant, the rate of the universe's expansion with unprecedented precision. By observing a specific class of pulsating stars called Cepheid variables in distant galaxies, astronomers using Hubble were able to calibrate the cosmic distance scale with far greater accuracy than ever before. This work was crucial for determining the age of the universe, which we now know to be 13.8 billion years. The telescope has also been an invaluable planetary scientist. It has tracked colossal storms on Jupiter and Saturn, provided breathtaking details of the swirling clouds of distant gas giants, and even directly imaged protoplanetary disks, the dusty, pancake-shaped rings of material around young stars where planets are in the process of formation. These observations gave us direct visual evidence of how solar systems are born. Furthermore, Hubble played a key role in the study of exoplanets. While it wasn't designed to find them, it has been used to analyze the atmospheres of giant planets orbiting other stars. By observing the minute dip in starlight as a planet transits in front of its host star, Hubble's spectrographs can dissect the filtered light to detect the chemical fingerprints of elements like sodium and even water vapor in alien skies. It provided some of the first compositional analyses of worlds beyond our solar system. Perhaps one of its most profound legacies is in charting the life cycle of galaxies. By comparing galaxies near and far, Hubble has allowed astronomers to assemble a grand narrative of galactic evolution. Its deep surveys show that galaxies in the early universe were much smaller, more irregular, and were frequently colliding and merging in a violent cosmic dance. Over billions of years, these mergers helped them grow into the majestic spirals and smooth ellipticals we see in the modern universe. Hubble has witnessed the death throes of stars in stunning detail, capturing the intricate, glowing shells of gas ejected by supernova and sun-like stars, showing us how stars recycle their material back into space to form new generations. The Pillars of Creation, one of its most famous images, is more than just a beautiful portrait of a stellar nursery in the Eagle Nebula. It is a dynamic snapshot of ongoing star birth, a place where intense radiation from newborn stars is simultaneously sculpting the gas and triggering the collapse of new stellar seeds. For over 3 decades, the Hubble Space Telescope has not just shown us the universe, it has told us its story. It transformed astronomy from a science of blurry black and white images into a field of breathtaking clarity and color, making the cosmos accessible and inspiring to millions. It demonstrated that with perseverance, technology, and a willingness to look deep into the darkness, we can uncover the ancient secrets written in light. Hubble gave us a front-row seat to the cosmic play, but the James Webb Space Telescope has handed us the script from the very first act. Imagine Hubble as a master painter who brought the universe into brilliant, sharp focus, revealing details we never knew existed. Now picture Webb as a master detective, equipped with tools to see not just the visible, but the hidden, the cold, and the ancient, the clues that have been fading for billions of years. Its primary mission is to peer into the infrared part of the spectrum, a domain of light that is invisible to our eyes and largely inaccessible to Hubble. This isn't just a minor upgrade, it's a fundamental shift in how we observe the cosmos, and it's all because of a simple, profound fact. The universe is expanding, and that expansion stretches light. As the universe grows, it pulls the fabric of space-time itself, and the light traveling through that space gets stretched along with it. For the most distant objects, the light that began its journey as visible or even ultraviolet light has been stretched so dramatically over its billions of years voyage that it arrives at our doorstep as infrared light. It's like the cosmic equivalent of a voice slowing down and dropping to a deep, low pitch as it moves away from you. For the very first galaxies, their light has been stretched so far into the infrared that they are completely invisible to telescopes designed for visible light. Hubble, for all its power, was listening to the universe with a limited range of hearing. Webb was built to hear the deepest notes, the lowest whispers from the edge of time itself. To do this, it needed to be more than just a bigger telescope. It had to be a completely new kind of observatory, designed from the ground up to be cold, stable, and incredibly sensitive. Its most obvious marvel is its golden mirror, a breathtaking honeycomb of 18 hexagonal segments that together span over 6.5 meters. This gives Webb a light collecting area about 6 times larger than Hubble's, allowing it to gather those incredibly faint, ancient photons with exquisite detail. But a large mirror alone isn't enough. Infrared light is essentially heat radiation. So to detect the faint heat signatures from the early universe, the telescope itself must be profoundly cold. Any warmth from the telescope would instantly overwhelm the delicate signals it's trying to capture. This is why Webb is stationed at Lagrange point 2, a gravitational balance point about 1.5 million kilometers from Earth. Here, the Sun, Earth, and Moon are all in the same direction, allowing the telescope to shield itself behind a tennis court-sized sun shield. This ingenious 5-layer kite separates the scorching heat of the Sun from the telescope, creating a permanent deep freeze on its instruments, chilling them to around -230 degrees Celsius. It's the ultimate sun hat, creating a sliver of eternal night in the vastness of space. With this unparalleled design, Webb is doing what no instrument has done before. It is capturing the light of the very first stars and galaxies to ever switch on, a period known as the cosmic dawn. We are now seeing galaxies as they were just a few 100 million years after the Big Bang, and the findings are already challenging our textbooks. Many of these infant galaxies appear surprisingly massive and well-structured, forming much earlier and faster than our models predicted. It's like expecting to see a toddler's first scribbles and instead finding detailed, complex paintings. This forces us to rethink the entire timeline of galaxy formation and the role of dark matter in seeding these structures so quickly. Webb isn't just showing us these galaxies as faint smudges. Its powerful spectrographs are dissecting their light, revealing their chemical composition. Astonishingly, some of these very early galaxies already show signs of heavy elements like oxygen and carbon, meaning that generations of stars had already lived, died in supernova, and enriched their surroundings with the elements for planets and life, all within the universe's first few percent of its current age. But Webb's vision isn't solely fixed on the distant past. It is also revolutionizing our search for other worlds. While Hubble could tell us an exoplanet was there, Webb can tell us what its air is like. When a planet transits in front of its host star, a tiny fraction of the star's light filters through the planet's atmosphere. Webb's exquisite infrared sensitivity allows it to analyze this filtered light, creating a detailed spectrum that acts as a chemical fingerprint. It can detect the presence of water vapor, methane, carbon dioxide, and even potential biosignatures like oxygen in the atmospheres of these distant worlds. It's the first telescope with the capability to seriously probe the atmospheres of Earth-sized rocky planets orbiting within the habitable zones of their stars, bringing us closer than ever to answering the age-old question of whether we are alone. From the birth of the very first galaxies to the potential for life on planets light years away, the James Webb Space Telescope is more than a successor. It is a gateway to a new era of discovery, translating the universe's faintest, oldest echoes into a story we are only just beginning to read. Yet for all the power of our orbiting observatories, the view from the ground remains profoundly important. and it's a view that is slowly fading from sight, not because of clouds, but because of our own doing. This is the challenge of light pollution, a problem that has less to do with the amount of light we use and everything to do with how carelessly we allow it to spill into the sky. Imagine you're in a vast, dark concert hall and a single musician on stage begins to play a soft, delicate melody. You can hear every note perfectly. Now imagine someone suddenly switches on a deafening industrial fan right next to you. The subtle music is completely drowned out, lost in the overwhelming roar. This is what light pollution does to astronomy. The faint, ancient light from distant galaxies and nebulae, which has traveled for millions or even billions of years, arrives at our telescopes as an incredibly weak signal. When that signal has to compete with the scattered glow of streetlights, parking lots, and office buildings from a nearby city, it's simply washed away. The contrast between the celestial object and the background sky is obliterated, rendering these cosmic wonders invisible. For professional astronomers, it means their ground-based observatories, often built at great expense on remote mountaintops for their pristine skies, are seeing their capabilities diminished as urban sprawl and its attendant glow creep ever closer. The faintest and most distant objects, the very ones that hold clues to the universe's earliest chapters, are the first to vanish from view. The impact, however, stretches far beyond the field of academic astronomy, seeping into the natural world and even our own well-being. Our planet's rhythms have been tuned for billions of years to the regular cycle of day and night, light and dark. Artificial light at night disrupts this fundamental rhythm with devastating consequences for ecosystems. Sea turtle hatchlings, instinctively drawn to the moonlight reflecting off the ocean, are now fatally disoriented by bright beachfront lighting, crawling inland instead of toward the sea. Millions of migratory birds who navigate by the stars become confused by the glow of cities, often circling illuminated buildings until they collapse from exhaustion or collide with windows. The entire food web is affected. Nocturnal animals that hunt or evade predators under the cover of darkness are left exposed, while populations of insects, crucial pollinators, are decimated as they swarm artificial lights until they die. For humans, the constant nighttime glow isn't just an aesthetic loss, it's a potential health concern. Exposure to artificial light after sundown, particularly the blue-rich light emitted by LEDs and screens, suppresses the production of melatonin, a hormone vital for regulating our sleep cycles. This disruption has been linked to sleep disorders, increased stress, and a higher risk for certain health problems, cutting us off from the natural circadian rhythm that has governed life on Earth since its beginning. We are, in a very real sense, polluting our own biology. The good news is that this is a problem with remarkably straightforward solutions, and it doesn't require us to plunge our cities into darkness. The goal isn't less light, it's better light. The core principle is simple. Light should be directed downward onto the ground where it is needed, not sideways or upward into the sky where it serves no purpose and causes harm. This is achieved through the use of fully shielded light fixtures, which have solid caps atop the bulb to prevent any light from escaping skyward. These well-designed lights illuminate streets and sidewalks just as effectively as unshielded ones, but they do so without creating glare that actually reduces visibility for drivers and pedestrians, and without contributing to the skyglow that hangs over our urban areas. Communities around the world are adopting dark sky-friendly lighting ordinances, and the International Dark Sky Association certifies parks and communities that make exceptional efforts to preserve their starry nights. These dark sky places, from national parks like Natural Bridges in Utah to entire towns like Flagstaff, Arizona, serve as living proof that we can have safe, well-lit communities while still maintaining our connection to the cosmos. They become havens not just for astronomers, but for anyone who wants to experience the awe-inspiring spectacle of a truly dark night sky, a view that was universal for all of human history until just a few generations ago. Preserving the night is about more than just protecting data for scientists or saving energy, though that is a significant benefit, as billions of dollars are wasted annually lighting up the empty sky. It is about safeguarding a fundamental part of our shared human heritage. For millennia, the star-strewn vault of the heavens has been our clock, our calendar, our compass, and the source of our deepest myths, stories, and scientific inquiries. It has inspired art, philosophy, and a sense of wonder that connects us to every generation that has ever looked up and asked questions. To allow that inheritance to be erased by careless lighting is to sever a vital link to our past and to the cosmos itself. By making simple, smart choices about how we light our world, we can ensure that the ancient messages carried by starlight continue to reach not only our telescopes but also our eyes, our hearts, and our imaginations, reminding us of our place in a vast and beautiful universe. But this cosmic speed limit is far more than just a number on a page. It is a fundamental rule woven into the very fabric of reality, a rule that has profound and mind-bending consequences for our understanding of time and space themselves. For centuries, physicists believed that space and time were absolute and separate, a fixed stage upon which the events of the universe played out. This common-sense view was completely upended in 1905 by a young patent clerk named Albert Einstein, whose theory of special relativity was built upon one deceptively simple postulate, that the speed of light in a vacuum is always the same for all observers, no matter how fast they are moving or in what direction. Imagine you are standing still and a friend rockets past you in a spaceship at half the speed of light. You both measure the speed of a beam of light emitted from the front of her ship. Common sense would suggest that from your perspective, the light should be traveling at its normal speed plus the speed of the spaceship. Astonishingly, that is not what happens. You will measure that light beam moving at exactly 299,792 kilometers per second. And even more incredibly, your friend inside the spaceship, who is moving incredibly fast, will measure the exact same speed for that same beam of light. This absolute constancy forces everything else, time, space, and mass, to become relative and flexible to compensate. This leads to two of the most famous and counterintuitive predictions in all of science: time dilation and length contraction. Time dilation means that a clock in motion relative to an observer will be measured to tick more slowly than a clock at rest. If your friend on that high-speed spaceship journey were to travel to a nearby star and back, she would have aged less than you who stayed on Earth. Her time literally passed more slowly from your perspective. This isn't a mechanical illusion. It is a fundamental property of time itself. At everyday speeds, this effect is immeasurably tiny, but it has been confirmed countless times with incredibly precise atomic clocks flown on airplanes, and is a critical correction factor for the satellites in our GPS network, which must account for the fact that their clocks run at a slightly different rate than those on the ground due to their orbital speed. Length contraction is the other side of the same coin. An object in motion measured along its direction of travel will appear shorter to a stationary observer. A spaceship traveling at a significant fraction of light speed would look compressed like a pancake to someone watching it zoom by, though everything would appear normal to the astronauts inside. These aren't just mathematical curiosities. They are the universe's way of ensuring that no matter how you are moving, when you measure the speed of light, you always get the same unwavering result. The stage of space and time itself bends and warps to uphold this one fundamental constant. This unwavering reliability is what makes light the ultimate cosmic historian. Because its speed is constant and finite, it acts as a perfect cosmic delay, allowing us to see directly into the past. When we look at the sun, we see it not as it is now, but as it was 8 minutes ago. If it were to suddenly vanish, we wouldn't know for 8 minutes. When we look at the Andromeda Galaxy, 2.5 million light-years away, we are seeing it as it was when early hominids were first walking on Earth. The light from the most distant galaxies captured by the James Webb Space Telescope has been on its journey for over 13 billion years, showing us what those galaxies looked like just a few 100 million years after the Big Bang. This time travel trick is only possible because the speed of light is a fixed and known quantity. It provides a direct one-to-one relationship between distance and look-back time. A light year is not just a unit of distance, it is a unit of time. This constancy means that the information carried by that ancient light has not been corrupted or altered in transit by a changing speed. It has been preserved with perfect fidelity across the eons. The redshift we measure from distant galaxies tells us how much the universe has expanded during the light's journey, but the unwavering speed of that light itself is what allows us to so precisely calculate just how long that journey has been. It is the universe's most reliable courier, a messenger we can trust absolutely to deliver its secrets from the deepest past, unchanged and unchangeable, right to our telescopes. Now, let's follow the journey of a single photon, one of the universe's most timeless travelers. Its story begins in the heart of a star, within a searing core where the immense pressure and temperature, reaching millions of degrees, force atomic nuclei together. In our own sun, this process is a relentless dance. Hydrogen atoms fuse to form helium, and in that transformative act, a tiny amount of mass is converted into a tremendous burst of pure energy, following Einstein's famous equation. This energy manifests as gamma-ray photons, the most energetic form of light. But our photon's journey to freedom is not a quick escape. It is born into a chaotic, dense environment where it is immediately absorbed by a nearby particle, only to be re-emitted a fraction of a second later. This absorption and re-emission happens countless times over tens of thousands of years, a random walk through the star's dense interior. A photon generated in the sun's core might take 100,000 years to finally reach its surface, having been passed around like a cosmic hot potato until it finally bursts into the relative emptiness of space, often having lost some energy and shifted into the visible light part of the spectrum. Once it breaks free from the star's gravitational embrace, the photon's journey truly begins. It now races across the vacuum of interstellar space at the ultimate speed limit, 299,792 kilometers per second. For most of its unimaginably long voyage, it will encounter nothing at all, sailing through the profound darkness between stars. But space is not entirely empty. It is peppered with wispy clouds of gas and dust. Our photon might be fortunate and pass through these regions completely unscathed, its path and its encoded information remaining perfectly pristine. However, it could also have a more eventful trip. It might slam into a lone hydrogen atom, be absorbed, and excite an electron to a higher energy level. A moment later, that electron will drop back down and our photon will be re-emitted, but now in a random direction. This scattering event doesn't destroy the photon, but it does erase the directional information of its origin. Alternatively, if the photon encounters a grain of interstellar dust, it could be reflected or refracted, again altering its path. Each of these interactions, while seemingly disruptive, actually leaves a forensic mark that astronomers can study to understand the composition and density of the material the light has passed through. The ultimate time capsule photons are those from the cosmic microwave background. These particles have been on an uninterrupted journey for nearly 13.8 billion years. They were set free during the epoch of recombination, when the young universe cooled enough for atoms to form, transforming from an opaque plasma into a transparent sea of hydrogen and helium. At that moment, these photons began streaming in every direction, and for the vast majority of them, their path has been almost perfectly straight and clear ever since. The expansion of the universe has stretched their wavelengths from visible light down into the microwave region, and they have cooled to just a few degrees above absolute zero. When we detect these photons with instruments like the Planck satellite, we are receiving a signal that has been traveling since the universe was a mere infant, a mere 380,000 years old. They have witnessed the entire history of cosmic expansion, flying through the growing vastness as galaxies formed and evolved around them, all without interacting with a single atom until they finally hit the detector in our telescopes. This makes their message the most pristine and direct record we have of the early universe. Every photon that arrives at our telescope, whether it's from a nearby star or a quasar at the edge of the observable universe, is a messenger with a unique biography. By carefully analyzing its properties, its exact energy, its polarization, and the subtle changes imprinted upon it during its long journey, astronomers can reverse engineer its history. They can determine what elements it passed through, how much the fabric of space itself has stretched during its flight, and ultimately, the conditions at its source billions of years ago. The light from a distant supernova, for example, doesn't just tell us about the explosion. The specific ways its light has been dimmed and reddened by intervening dust and gas provide a detailed map of the material between galaxies. This incredible resilience of information is what makes light the universe's most reliable historian. Each photon is a tiny packet of data, an immortal traveler whose journey across space and time ends by delivering its ancient secrets directly into our hands, allowing us to piece together the story of everything. For centuries, the question of whether we are alone in the universe was a matter of pure philosophy and speculation. Today, it is a rigorous scientific pursuit, and the key to answering it lies in the same cosmic messenger that reveals the universe's past: light. We are no longer just looking for little green men or listening for random radio greetings. We are using advanced tools to scan the atmospheres of distant worlds for the chemical fingerprints of life itself. This search focuses on two primary strategies: hunting for biosignatures, which are signs of biological processes, and technosignatures, which are evidence of advanced technology, and both rely entirely on our ability to capture and decode light. The most promising method for finding biosignatures is called transmission spectroscopy, and it works like a cosmic medical exam. When an exoplanet passes directly in front of its host star from our point of view, an event known as a transit, a tiny fraction of the star's light filters through the planet's atmosphere on its way to us. As this light passes through this thin, gaseous envelope, molecules within the atmosphere absorb specific wavelengths of light, leaving behind a unique set of dark lines in the star's spectrum. It's as if the planet's atmosphere imprints its own barcode onto the starlight. By meticulously decoding this barcode, astronomers can identify the gases present. The presence of certain gases in combination, especially those that are chemically unstable and would quickly vanish without a constant replenishing source, can be a powerful hint of life. On Earth, our atmosphere is rich with oxygen and methane, two gases that readily react with each other and would disappear if not continuously regenerated by photosynthesis and biological processes like digestion. Finding a similar unstable cocktail on a distant, rocky world orbiting within its star's habitable zone where temperatures could allow for liquid water would be one of the most compelling indicators we could hope for. This is where instruments like the James Webb Space Telescope become revolutionary. While previous telescopes could tell us an exoplanet was there, Webb's powerful infrared capabilities and massive mirror allow it to perform this delicate spectroscopic analysis on the atmospheres of Earth-sized planets for the first time. It can detect the subtle dimming caused by the transit and then dissect the filtered starlight to search for the telltale signs of water vapor, carbon dioxide, methane, and yes, even oxygen. Each successful observation is a painstaking process, often requiring multiple transits to gather enough photons for a clear signal. But the results are already beginning to paint pictures of these alien worlds, revealing them to be everything from barren rock to puffy gas giants with exotic, vaporized rock clouds. Alongside the search for these natural byproducts of biology, there is a parallel quest for evidence of intelligence, technosignatures. This search involves scanning the cosmos for light that has been deliberately structured or altered. The most long-standing effort is SETI, the search for extraterrestrial intelligence, which primarily listens for narrow-band radio signals. The logic is that while the universe is filled with natural radio noise, a powerful, focused transmission on a very specific frequency would stand out as clearly artificial, a beacon purposefully designed to announce we are here. But the search for technosignatures has expanded far beyond radio. Astronomers now also look for directed laser pulses that could be used for interstellar communication, a concept known as optical SETI. They even consider the possibility of detecting megastructures, like hypothetical energy-collecting Dyson spheres, which would alter the light from a star in detectable ways, perhaps by causing unusual dips in its brightness or by emitting excess infrared radiation from the absorbed energy. While this might sound like science fiction, it is a serious, data-driven endeavor that uses the same principles of careful observation and analysis. Both of these approaches, the search for biosignatures and technosignatures, are united by their reliance on light as the fundamental carrier of information. They transform the question of extraterrestrial life from a fantasy into a forensic science. We may never physically visit these distant worlds within our lifetimes, but by reading the light that has interacted with them, we can explore their potential for life from unimaginable distances. Every photon collected is a potential clue, a piece of a puzzle that could ultimately tell us whether the intricate chemistry we call life is a rare fluke on our pale blue dot or a common symphony playing throughout the cosmos. But the quest to decode the universe's ancient light doesn't end with Webb. In fact, we are on the cusp of a new golden age of astronomy, driven by a wave of next-generation telescopes and revolutionary technologies that will push our vision further and with greater clarity than we ever thought possible. These are not just incremental upgrades, they are monumental leaps that will fundamentally change our understanding of the cosmos, allowing us to see the first stars ignite, to directly image Earth-like worlds, and to map the hidden scaffolding of dark matter itself. The future of cosmic exploration is being built right now, on remote mountaintops and in clean rooms around the world, and it promises to reveal secrets hidden within light that has been traveling for over 13 billion years. Leading this charge on the ground is a truly colossal endeavor, the Extremely Large Telescope, or ELT. As its name implies, this is a project of extreme scale and ambition. Under construction atop a mountain in Chile's Atacama Desert, the ELT will feature a primary mirror a staggering 39 meters across, a mosaic of nearly 800 individual hexagonal segments. To put that in perspective, its light-gathering area will be over 250 times larger than that of the historic Hubble Space Telescope. This immense size translates directly into breathtaking resolution and sensitivity. With its advanced suite of instruments, the ELT will be able to directly image exoplanets, separating their faint light from the blinding glare of their host stars to analyze their atmospheres for signs of habitability. It will peer into the hearts of distant galaxies, witnessing their formation in the early universe, and it will measure the precise expansion rate of the cosmos with unprecedented accuracy, potentially solving the ongoing tension in our measurements of the Hubble constant. The ELT will essentially act as a time machine, collecting the faintest photons from the most distant objects to provide a detailed, high-definition view of the cosmic dawn. While the ELT conquers the challenges of Earth-based observation, a new space-based pioneer is preparing to join the fray, the Nancy Grace Roman Space Telescope. Named after NASA's first chief astronomer, this observatory is often described as the wide-eyed cousin to the deep-seeing James Webb. Where Webb focuses intensely on small patches of sky for days at a time, Roman will have a field of view 100 times larger than Hubble's, allowing it to survey vast swaths of the universe at an incredible speed. Its primary mission is to tackle the twin mysteries of dark energy and dark matter through three powerful techniques. It will conduct a massive high-resolution survey of the sky, measuring the shapes and distances of billions of galaxies to map the distribution of dark matter via weak gravitational lensing with exquisite detail. It will discover thousands of new exoplanets using its sophisticated coronagraph, a device that blocks starlight to reveal orbiting worlds, and it will scan for the telltale light curves of Type Ia supernova across cosmic time, adding more data points to our understanding of the universe's accelerating expansion. Roman's wide-field, rapid-fire approach will provide the broad context, the cosmic senses, that will help us understand where to point our more focused telescopes for deeper study. A critical innovation that makes all of this ground-based discovery possible is the continued revolution in adaptive optics. For centuries, Earth's shimmering atmosphere has been the enemy of astronomers, blurring the light from stars and galaxies into frustrating smudges. Adaptive optics is the technological wizardry that fights back. These systems use a powerful laser to create an artificial guide star high in the atmosphere. Sensors then measure how this artificial star's light is distorted as it passes through the turbulent air. A computer calculates the corrections needed and sends instructions hundreds of times per second to a deformable mirror that sits in the telescope's light path. This mirror flexes and bends to precisely counteract the atmospheric distortion, resulting in images that are as sharp as if the telescope were in space. The latest systems are so advanced they are approaching near-perfect correction, allowing ground-based telescopes like the ELT to rival and even surpass the resolution of their space-based counterparts for certain types of observations, all while benefiting from the ability to build much larger mirrors on the ground. Beyond building bigger telescopes, astronomers are also perfecting the art of combining them through a technique called interferometry. This process links multiple individual telescopes together to act as a single, gigantic instrument with a resolution equivalent to a mirror as wide as the distance between them. The Event Horizon Telescope, which produced the first image of a black hole, is a stunning example of this, creating a virtual Earth-sized dish. The next generation of optical and infrared interferometers will take this to a new level, allowing us to see unprecedented detail on the surfaces of distant stars, to probe the inner regions of accretion disks around black holes, and to directly measure the diameters of stars in other galaxies. It's a way of achieving impossible resolution without having to build a single, impossibly large piece of glass. perhaps the most exciting development is the move beyond light alone. While photons will always be our primary cosmic messengers, the future of astronomy is multi-messenger. We are now learning to hear the universe through gravitational waves, ripples in space-time caused by cataclysmic events like colliding black holes. Observatories like LIGO and Virgo detect these waves, and when a gravitational wave signal is matched with a flash of light observed by telescopes, we get a complete picture of the event, from its gravity to its radiation. Similarly, detectors are now catching neutrinos, ghostly, nearly massless particles that stream through the universe, often born in the same violent explosions as light and gravitational waves. By combining the information from light, gravitational waves, and neutrinos, we are no longer just watching the universe. We are experiencing it with all of our senses, piecing together a richer, more complete story of how it works, from the smallest particles to the largest structures, all driven by our relentless pursuit of the ancient echoes carried across the cosmos. This incredible ability to see into the past isn't just a philosophical curiosity. It's the most powerful tool in an astronomer's kit, a practical function built into every telescope ever made. We don't need a fictional DeLorean with a flux capacitor to travel through time. We have observatories. Every time we point a telescope at the sky, we are activating a genuine time machine. The mechanism is elegantly simple. Look farther away and you automatically see further back in time. This is because the light from more distant objects has been traveling for a longer period to reach us. A photon that left the Andromeda galaxy 2.5 million years ago is only just arriving at our eyes now, showing us what that galaxy looked about the time our earliest human ancestors were beginning to walk the Earth. The light from a quasar 10 billion light-years away is a dispatch from an era when our solar system didn't even exist. By carefully choosing where to look and how deeply to gaze, astronomers can effectively choose which chapter of the universe's history they want to read. This principle allows us to construct a detailed cosmic timeline, a family album of the universe from its infancy to the present day. We can't watch a single galaxy evolve in real time. That would take billions of years, but we can see snapshots of different galaxies at different ages. It's like walking into a portrait gallery where the subjects are arranged not by artist but by age. On one wall, we have the nearby modern galaxies like our own Milky Way and Andromeda, showing us the universe in its mature, settled state. As we walk further into the gallery, we see galaxies that are farther away and therefore younger. Their portraits show them to be smaller, more chaotic, and often in the process of colliding and merging. Their light is bluer, indicating ferocious rates of new star birth. In the very deepest frames from the Hubble and Webb telescopes, we see the most distant walls of the gallery, the toddler galaxies, as they were just a few 100 million years after the Big Bang. These are not the grand spirals we know today, but tiny, clumpy proto-galaxies, glowing with the intense light of their first massive stars. By comparing all these portraits, we can piece together the entire story of galactic evolution, from birth to maturity, without ever having to wait around. This layered view of time is absolutely crucial for testing and refining our theories about how the cosmos works. For example, our understanding of the universe's expansion is built upon this principle. By measuring the redshift of galaxies at various distances, and thus from various epochs, we can track how the expansion rate has changed over billions of years. It was this comparative approach that revealed the shocking acceleration driven by dark energy. Similarly, we can study the growth of supermassive black holes. In nearby galaxies, we often find these behemoths sleeping quietly at the center. but when we look at their counterparts in the early universe, we see them as brilliant quasars, actively feasting on gas and growing rapidly. This tells us that the most active growth phase for black holes occurred in the distant past, a fact we could only learn by looking back in time. Even the very elements that make up our world have a history written in light. By analyzing the spectra of extremely distant, ancient galaxies, astronomers have found that the earliest stars had very few heavy elements. The universe was primarily hydrogen and helium. It was only after generations of stars lived, died in supernova, and enriched the cosmos that later generations of stars and planets could form with the diversity of elements we see today. We are literally watching the universe become more chemically complex over time. Ultimately, this transforms our understanding from a static picture into a dynamic, unfolding movie. Light doesn't just show us where things are, it shows us when they were and how they have changed. It provides a continuous visual record of cosmic history, allowing us to witness the grand narrative of structure formation, from the first tiny ripples in the primordial plasma to the vast, glittering web of galaxies we see today. This ever-deepening view answers fundamental questions about our origins while simultaneously posing new and more profound ones about our ultimate destiny, all thanks to the timeless journey of light acting as our faithful cosmic historian. Yet this connection to a past that may no longer exist raises a profound question about the nature of reality itself. When we observe a galaxy a billion light-years away, we are not seeing an object as it is now, but as it was a billion years in the past. For all we know, that galaxy may have long since collided with another, or been consumed by a central black hole, or dissipated entirely. So what are we truly observing? Are we studying reality, or are we studying history? This places astronomy in a unique category among the sciences. It is a form of archaeology, where the artifacts are not buried in the ground but are written in light, and the past we are excavating is not of human civilization, but of existence itself. Our entire view of the cosmos is therefore a mosaic of different eras, a patchwork quilt of moments stitched together from across billions of years. The night sky is not a single, coherent picture of the present, but a layered portrait of deep time, where the past and present coexist within our field of view, challenging our very definition of what is real and what is memory. This tangible link to the past also reshapes our understanding of time's arrow and our place within its flow. In our daily lives, we experience time as a linear progression from past to future, a one-way street where moments vanish into history as soon as they occur. But light from the cosmos offers us a different perspective. It suggests that the past is not lost or inaccessible. It is all around us, traveling through space, waiting to be captured and decoded. In a very real sense, the past is not gone, it is simply elsewhere. This idea echoes in the philosophical concept of the block universe, where time is not a flowing river but a static, four-dimensional structure encompassing all of space and time, from the Big Bang to the far future. Within this view, the past, present, and future all exist simultaneously, and our perception of time's passage is merely an illusion of consciousness. When we observe ancient light, we are not just looking back in time. We are touching a different part of this eternal structure, making contact with a reality that is always there, even if we normally perceive it as gone. This cosmic perspective inevitably leads to a deep sense of humility and wonder. To realize that the photons striking a telescope mirror have been traveling in solitude since before our planet even formed, carrying a message from an epoch when the universe was young, is to feel both incredibly small and profoundly connected. We are temporary beings on a small rock orbiting an average star in a typical galaxy. yet we possess the ability to reach out across the vastness and comprehend the story of creation. This quest for understanding is not a detached clinical exercise. It is a fundamental part of what it means to be human. Our curiosity, our drive to explore and to know, is itself a product of the very universe we seek to understand. The carbon in our cells, the oxygen we breathe, the iron in our blood, all were forged in the hearts of long-dead stars and scattered across space by supernova explosions. We are not just observers of the cosmos, we are a part of it, a way for the universe to know itself. The light we study is not an external phenomenon, it is our inheritance. Ultimately, the philosophical journey guided by light enriches the scientific one, adding layers of meaning to the data and the equations. It reminds us that every measurement of redshift, every spectrum analyzed, every distant galaxy catalogued, is more than just a data point. It is a sentence in a story that began nearly 14 billion years ago. This story tells of forces beyond human comprehension, of timescales that dwarf our history, and of a universe that is both terrifyingly vast and strangely intimate. By contemplating the light that carries these ancient echoes, we engage in a dialogue with the cosmos, one that challenges our assumptions, expands our imagination, and deepens our appreciation for the beautiful, mysterious, and seemingly impossible fact that we are here at all, able to look up and ask these questions in the first place. It's easy to view our quest to understand the cosmos as a purely intellectual exercise, a beautiful but abstract pursuit with little bearing on our daily lives. Yet the truth is far more remarkable. The technologies developed to capture and decode the universe's ancient light have a profound habit of spinning off into innovations that reshape our world in the most practical ways. The drive to peer deeper into space doesn't just satisfy our curiosity. It consistently delivers tangible benefits that improve health, redefine communication, and enhance our daily experiences right here on Earth. Consider the Hubble digital camera, a device that now lives in nearly every pocket. The heart of every smartphone camera and digital SLR is a charge-coupled device, or CCD. This technology wasn't invented for vacation snapshots or social media posts. It was developed in the late 1960s at Bell Labs specifically for astronomy. Scientists needed a far more efficient way to capture light than photographic plates, which waste over 99% of the photons that hit them. A CCD is incredibly sensitive, capable of detecting and recording almost every single photon that strikes its surface. This allows astronomers to create detailed images of incredibly faint, distant galaxies that would otherwise be completely invisible. That same sensitivity is what allows your phone to take a clear picture in a dimly lit room. The astronomical need to capture every precious photon from the edge of time directly enabled the revolution in digital imaging that now connects us visually and documents our lives. The influence extends even into the medical field, saving lives in ways that directly trace back to the stars. The development of magnetic resonance imaging, or MRI, technology is deeply indebted to the work of radio astronomers. The key to MRI is detecting the faint radio signals emitted by the nuclei of atoms within the human body when they are placed in a strong magnetic field. The mathematical techniques needed to process these weak, complex signals, to transform raw radio data into a clear, detailed, three-dimensional image of our internal organs, were pioneered by astronomers trying to clean up the noisy radio signals they received from distant pulsars and quasars. The algorithms that filter out cosmic static to reveal the structure of a galaxy are the very same ones that filter out biological noise to reveal a tumor or a torn ligament. A tool designed to explore the mysteries of the universe now serves as one of our most powerful instruments for diagnosing disease and healing the human body. And then there's the very infrastructure of our modern connected world, the global network of fiber optic cables that carry our voices, our videos, and our data at the speed of light. The science behind this technology, transmitting information through thin strands of glass, was supercharged by astronomers' relentless pursuit of clearer vision. To overcome the distorting shimmer of Earth's atmosphere, astronomers developed adaptive optics systems which use lasers and deformable mirrors to correct for turbulence in real time. The research into how light propagates through and interacts with different materials to minimize distortion was crucial for refining the glass fibers and laser signals used in telecommunications. The quest for a clearer view of the cosmos directly helped engineer a clearer path for the light that carries the internet, enabling the high-speed, high-bandwidth communication that defines the 21st century. Even the way we process and understand vast amounts of information owes a debt to the stars. Astronomy is fundamentally a science of big data. A single night of observation on a major telescope can generate terabytes of information. To sift through this deluge of data to find distant galaxies, subtle planetary transits, or the faint whispers of the cosmic microwave background, astronomers had to create sophisticated image processing software and powerful data compression algorithms long before they became commonplace. These techniques are now ubiquitous, used in everything from enhancing medical scans and satellite weather imagery to the facial recognition software on your phone and the video streaming services that adjust quality based on your internet connection. The challenge of finding a cosmic needle in a digital haystack forced the development of tools that now help us navigate and make sense of our own world's information explosion. This pattern is a powerful reminder that fundamental, curiosity-driven research is not a luxury. It is an investment in our future. When we fund the construction of a giant telescope or the launch of a new space observatory, we are not just buying knowledge about black holes and distant galaxies. We are investing in a research and development engine that has a proven, decades-long track record of spinning off unforeseen technologies that create new industries, cure diseases, and connect humanity. The drive to understand the light from the cosmos consistently illuminates our path forward, proving that the most profound exploration of the universe out there inevitably leads to profound advancements right here at home. One of the most persistent myths about our view of the cosmos is the idea that when we look up at the night sky, we are seeing the universe as it truly is in this very moment. This feels intuitively right after all. When we turn on a lamp, the room illuminates instantly, but this everyday experience betrays the reality of the cosmic scale. The truth is far more fascinating. We are perpetual time travelers, and the night sky is a grand historical archive. That twinkling star in the constellation Orion might be Betelgeuse, and the light entering your eye tonight left the surface of that dying star around the time the Normans were conquering England. You are not seeing Betelgeuse as it is now. You are witnessing a 600-year-old snapshot of it. This isn't a flawed or outdated view. It is our only window into the past. Every celestial object is seen at a different point in its history, creating a collage of moments across billions of years. Far from being a limitation, this delay is the very foundation of cosmology, allowing us to literally observe the evolution of the universe by looking outward and therefore backward in time. Another common misconception is that light, as a wave, requires a medium to travel through, much like sound needs air or water. This was once a serious scientific hypothesis known as the luminiferous ether, a mysterious substance thought to permeate all of space. The famous Michelson-Morley experiment in the late 19th century sought to detect this ether by measuring the speed of light in different directions as Earth moved through space. To everyone's astonishment, they found absolutely no evidence for it. The speed of light was constant in every direction, regardless of Earth's motion. This null result was a pivotal moment in physics, leading directly to Einstein's theory of special relativity, which established that light is unlike any other wave. It does not need a medium. Photons are self-propagating disturbances in the electric and magnetic fields that can travel perfectly through the utter vacuum of space. This is why light from distant galaxies can journey for billions of years without being slowed or scattered. It rides the fabric of space-time itself unimpeded. The phenomenon of redshift is also frequently misunderstood, often simplified as just the cosmic version of the Doppler effect, the same thing that makes a siren's pitch drop as it races past you. While the Doppler effect does cause a shift in the wavelength of light for objects moving through space, this is only a small part of the story, especially on the grandest scales. The primary cause of the redshift we see from distant galaxies is not their motion through space, but the expansion of space itself. Imagine a photon of light as a wave traveling along a rubber band. If you stretch that rubber band while the wave is in transit, the wave itself gets stretched, lengthening its wavelength and making it redder. This is cosmological redshift. The space between galaxies is expanding, and as light voyages across that growing divide, its wavelength is stretched along with it. The greater the distance the light has traveled, the more it has been stretched, which is why redshift becomes a direct measure of both distance and look-back time. Conflating this with the simple Doppler effect misses the profound implication that it is the very fabric of the universe that is dynamically changing. Perhaps one of the most visually intuitive yet incorrect beliefs is that space is full of obstacles that block our view, creating an impenetrable wall at some distant point. We hear that the universe is 13.8 billion years old, and so we assume we can only see 13.8 billion light years away. This is not the case. Due to the relentless expansion of the universe, the distance to the most distant objects we can observe is actually much, much farther. The light from the cosmic microwave background has been traveling for about 13.8 billion years to reach us. But in that time, the space it has been traveling through has expanded tremendously. The source of that light is now estimated to be about 46 billion light years away from us. The observable universe is thus a sphere with a radius of roughly 46 billion light years centered on us. There is no literal edge in the traditional sense. There is simply a horizon beyond which light has not had enough time to reach us yet. This horizon is not a physical barrier but a temporal one, and as time passes, more light arrives, slowly increasing the size of our observable universe and bringing new galaxies into view. Finally, there's a notion that looking back in time like this is somehow an inferior or indirect way to do science, that we can't truly trust what we see because it's just history. This couldn't be further from the truth. In every other historical science, like geology or paleontology, we reconstruct the past from static clues, fossils, and rock layers that have been altered over eons. But in cosmology, the past is actively being delivered to us pristine and unchanged by the light itself. A spectrum of a distant quasar isn't an interpretation of a fossil. It is the direct, unaltered data from an era when the universe was young, a data stream that has been traveling uninterrupted for billions of years. It is the most direct evidence possible. Correcting these myths isn't just about factual accuracy. It's about opening ourselves up to the true wonder of our place in the cosmos. We are not passive observers of a static stage. We are active participants in a dynamic, evolving universe, equipped with the ability to receive and decode ancient messages written in light, allowing us to witness the grand story of creation unfold. Long before we had spectrographs to dissect starlight or equations to define its speed, humanity held a deep and abiding reverence for light itself. It is a thread woven through the very fabric of our history, a universal symbol that transcends cultures and epochs. For our earliest ancestors, the daily victory of the sun over the darkness was not just a celestial event. It was a drama of life and death, a reason for hope and a cause for worship. In ancient Egypt, the sun god Ra was the supreme deity, the creator of all things, who sailed his solar bark across the sky each day, battling the serpent of chaos to ensure the world's survival. His light was synonymous with order, truth, and life itself. Similarly, in countless other cultures, from the Greeks with Apollo's chariot to the Hindu reverence for Surya, light was deified, representing the ultimate power and creative force of the cosmos. This association of light with the divine and the act of creation is one of our oldest and most shared human narratives, a testament to its fundamental importance to our existence. This fascination quickly evolved beyond mythology into the realm of philosophy and early science, where light became a metaphor for knowledge and understanding. The concept of enlightenment is central to many of the world's spiritual traditions. In Buddhism, achieving enlightenment means awakening to the true nature of reality, stepping out of the darkness of ignorance into the light of wisdom. In the Western tradition, the Age of Enlightenment itself was named for this very metaphor, a period where thinkers championed reason, science, and intellectual interchange over superstition and tradition, aiming to illuminate the human condition. This intellectual shift was profoundly literalized with a simple yet revolutionary invention, the telescope. When Galileo Galilei first pointed his spyglass towards the heavens in 1610, he wasn't just magnifying distant points of light, he was shining a lamp on a Chinese letter universe. His observations of the craters on the moon, the moons of Jupiter, and the phases of Venus provided irrefutable evidence that the heavens were not a perfect, unchanging realm, but a physical place that could be studied and understood. The light captured by his primitive lenses ignited a scientific revolution, forever changing our relationship with the cosmos and demonstrating that the path to true knowledge was through empirical observation of the light all around us. This cultural and scientific journey is reflected beautifully in our art and literature, where light is perpetually used to convey emotion, meaning, and the sublime. Renaissance painters like Caravaggio mastered the technique of chiaroscuro, the dramatic contrast between light and shadow, to create breathtaking depth and focus, often using light to symbolize divine intervention or moral clarity in a scene. Centuries later, the Impressionist artists became obsessed with light itself, striving to capture its fleeting effects on water, landscapes, and city streets, studying how it fractured and transformed the perception of color and form. In literature, light is a perennial symbol of hope, truth, and discovery. From the guiding beacons in epic poems to the green light at the end of Daisy's dock in The Great Gatsby, light serves as a powerful narrative device, representing our deepest yearnings and aspirations. This artistic engagement shows that our drive to understand light is not merely clinical, it is deeply emotional and creative. We are not just analyzing photons, we are grappling with a phenomenon that is central to our aesthetic and spiritual experience of the world. Today, this ancient fascination continues unabated, finding new expression in our modern rituals and our relentless push for innovation. We still gather to watch the sunrise on the solstice. We fill our homes with festive lights during celebrations, and we speak of public figures being in the spotlight. Our cultural narrative of light has seamlessly merged with our scientific one. The same awe that inspired cathedrals to be built with magnificent stained glass windows flooding the interior with celestial colors now inspires us to build colossal telescopes on remote mountaintops and launch them into the void of space. We are still driven by that same fundamental desire to connect with the light, to understand its source, and to comprehend our place within its grand story. This rich cultural history does not diminish the scientific facts, it enriches them. It reminds us that the quest to decode the universe's ancient echoes is not a cold, detached calculation. It is the latest chapter in a timeless human saga, a continuation of our eternal dialogue with the light that has always defined our world, both literally and symbolically. We are the heirs to both the shamans who prayed to the sun and the philosophers who sought enlightenment, now equipped with the tools to finally read the messages that light has been carrying for billions of years. Yet for all its incredible power as a cosmic messenger, light itself has fundamental limits, boundaries to its knowledge that even our most advanced technologies cannot overcome. These are not simply current technological hurdles we might one day leap. They are hard barriers woven into the very fabric of physics, reminding us that the universe will always hold secrets just beyond our grasp. The most profound of these boundaries is the very edge of our sight, a horizon not in space but in time. We live in a universe that is 13.8 billion years old, and because light has a finite speed, we can only see the parts of it from which light has had time to reach us. This creates a sphere around us called the observable universe, a bubble of visibility with a radius of about 46 billion light-years. This vast distance is larger than the age of the universe because space itself has been expanding during the time the light was in transit, stretching the distance between us and the source of that ancient light. But what lies beyond that bubble? The answer is we fundamentally cannot know. There is almost certainly more universe, much more extending far beyond what we can see. But any light from those regions hasn't had enough time to reach us since the Big Bang, and it never will do to the accelerating expansion of the cosmos. Those realms are forever hidden from our view, leaving us to wonder about the true, full scale of existence, which might be infinite for all we know. Then there are the places where light itself is captured and silenced, creating permanent black boxes in the cosmos. Black holes represent the ultimate victory of gravity over light. Their gravitational pull is so intense that at a certain boundary called the event horizon, the escape velocity exceeds the speed of light. Since nothing can travel faster than light, anything that crosses that point, including light itself, is lost forever to the outside universe. A black hole reveals its presence only indirectly, through its gravitational influence on nearby stars and gas, and through the ghostly glow of radiation from its superheated accretion disk. But the interior, the singularity itself, is completely hidden. The laws of physics as we understand them break down at that point of infinite density. What happens to matter and information that falls in? Does it simply cease to exist? Is it somehow preserved in a way we cannot perceive? These are questions that light, by its very nature, can never answer for us because it cannot bring any information out from behind that final curtain. This veil over reality extends down to the very smallest scales, governed by the bizarre rules of quantum mechanics. Here, light is not just a messenger, it is an active participant that fundamentally alters what it measures. The Heisenberg uncertainty principle states that there is a fundamental limit to the precision with which we can know certain pairs of properties, like a particle's position and its momentum. The act of observing a particle of shining light on it to pinpoint its location involves striking it with a photon. This interaction necessarily transfers energy and disturbs the particle, changing its momentum in an unpredictable way. The more precisely you try to measure its position, the less you can know about where it's going. This isn't a limitation of our instruments, it is a basic property of the universe. At the quantum level, reality is inherently fuzzy, a world of probabilities and waves rather than certainties and particles. Light is the tool we use to probe this realm, but it also defines the ultimate resolution of our measurement, ensuring that a core layer of uncertainty will always remain. These boundaries are not failures of science, they are its guideposts, humbly showing us the edges of the map beyond which be dragons. They teach us that the universe is under no obligation to be completely comprehensible to the human mind. The fact that there are questions that might remain forever unanswered is not a reason for despair, but a source of endless wonder and a catalyst for curiosity. It pushes us to develop new tools, to conceive of new theories, and to imagine possibilities beyond our current understanding. It reminds us that for all we have learned from decoding the ancient light that fills the cosmos, the greatest mystery may always be the vast, unseen unknown that lies just beyond its reach. The quest to unravel the universe's deepest mysteries is no longer a solitary pursuit confined to a single observer at a telescope eyepiece. The scale of the questions we're asking and the sheer volume of data required to answer them has grown so immense that it demands a collective effort. This is the era of collaborative astronomy, a global endeavor where the shared goal of decoding light's ancient secrets transcends national borders, political differences, and institutional rivalries, uniting humanity in a common project of cosmic discovery. Think of it not as many different teams working in isolation, but as a single, distributed brain across the planet, with each observatory, each researcher, and each supercomputer acting as a neuron firing in concert to build our shared understanding. Perhaps the most stunning example of this global brain in action is the Event Horizon Telescope project. Its goal was audacious: to capture the first ever image of a black hole's event horizon, the point of no return for light itself. The target was the supermassive black hole at the heart of the galaxy M87, a behemoth weighing in at 6.5 billion times the mass of our Sun. But to see it, astronomers needed a telescope virtually the size of Earth itself, an impossibility to build. So they did the next best thing. They synchronized a global network of 8 existing radio observatories, from the high deserts of Chile and Arizona to the icy peaks of Hawaii and Spain, and even the South Pole. For a few days in April 2017, these far-flung facilities acted as a single, planet-sized instrument. Each site recorded petabytes of raw data onto stacks of high-speed hard drives, which were then physically flown to central processing centers in the United States and Germany. The reason for this sneakernet approach: the datasets were so colossal that transferring them over the internet would have taken years. Teams of scientists then spent years painstakingly correlating the data, using atomic clocks to ensure perfect synchronization, and slowly, painstakingly, assembling the now iconic image of a fiery ring of light surrounding a dark shadow, the black hole itself. No single country, no single university could have ever achieved this alone. It was a triumph of global coordination, a testament to what we can accomplish when we pool our resources and our curiosity. While the EHT provides a breathtakingly detailed look at a single, monstrous object, other collaborations aim for an almost unimaginable breadth. The Sloan Digital Sky Survey began mapping the universe in 2000, using a dedicated 2.5-meter telescope in New Mexico to systematically image and measure the spectra of millions of celestial objects. Its latest phase, SDSS-5, is even more ambitious, aiming to create the largest ever three-dimensional map of the universe, charting the spectra of over 6 million galaxies and quasars. This isn't the work of a small, closed group. The survey is operated by a consortium of hundreds of scientists at dozens of institutions around the world. But more importantly, the data isn't hoarded. From the very beginning, SDSS has championed a policy of making its vast datasets publicly available to anyone, anywhere. This commitment to open data has democratized astronomy. A high school student in India, an amateur astronomer in Brazil, or a researcher at a small college without a major telescope can all access the same precise measurements that are available to a professor at Harvard or Oxford. This has led to thousands of scientific papers, many from entirely unexpected quarters, discovering everything from new types of quasars to bizarre stellar anomalies. The light collected by one telescope in New Mexico becomes a shared resource for the entire world, accelerating discovery at a pace that would be unthinkable if every research group had to gather its own data from scratch. This culture of sharing extends beyond raw data to the very tools needed to analyze it. The software used to process images, model gravitational lensing, or simulate galaxy formation is increasingly developed as open-source projects. Platforms like GitHub host thousands of astronomical code libraries, allowing a researcher in South Africa to build upon an algorithm written by a team in Japan, who in turn adapted a statistical technique developed by a student in Norway. This collaborative coding prevents redundant work and ensures that the best methods become a common standard, elevating the entire field. Furthermore, the challenges of processing this big data deluge have spurred partnerships beyond academia. Astronomers are now working closely with computer scientists at companies like Google and IBM, adapting machine learning and artificial intelligence techniques originally designed for recognizing faces in photos or optimizing search engines to instead identify distant galaxies in telescope images or find subtle signals of exoplanets in starlight. This cross-pollination of ideas is solving problems faster than either community could alone. What drives this remarkable spirit of cooperation? It's the recognition that the universe is our collective heritage. The light from a distant supernova or a far-off galaxy doesn't belong to any one nation. It's a message sent to all of Earth, and it requires all of us to decipher it. These monumental projects, from the global synchronized dance of the Event Horizon Telescope to the patient, open-ended mapping of the Sloan Survey, show that our deepest hunger for understanding can bring out the very best in us. They prove that when we choose to look up together, we can overcome the most daunting technical challenges and piece together the grand puzzle of cosmic history, revealing that the secrets carried by light are indeed a shared inheritance for all of humanity. It might seem like a giant leap from studying the faint whispers of ancient galaxies to monitoring the health of our own planet, but the connection is both direct and profound. The very same techniques astronomers developed to decode the light from distant stars have been turned back towards Earth, creating an entirely new field of science that uses our planet's own reflected light as a vital diagnostic tool. This isn't just a happy accident. It's a powerful demonstration of how the quest to understand the cosmos consistently delivers benefits that help us protect our fragile home. By analyzing the specific wavelengths of sunlight that bounce off Earth's surface and atmosphere, satellites equipped with advanced spectrometers can now track the intricate dance of our global climate system, measure the impact of human activity, and provide the hard data needed to confront some of our greatest environmental challenges. Think of it like this: to an astronomer, a distant star is a single point of light. The only way to understand its composition, temperature, and motion is to break its light into a highly detailed spectrum, reading the unique fingerprint of absorption and emission lines. Now imagine applying that exact same principle to our entire planet. Instead of a single point, we have a complex, swirling mosaic of ocean, land, ice, and clouds. A satellite in orbit doesn't just take a picture, it acts as a giant spectrometer in the sky, capturing the sunlight reflected from every patch of Earth below it. Each type of surface and each gas in the atmosphere interacts with light in a unique way, absorbing some wavelengths and reflecting others. By carefully analyzing this reflected spectrum, scientists can identify and quantify what's down there and what's up there with astonishing precision. This is where missions like NASA's Terra satellite become absolute heroes of Earth science. Launched in 1999, Terra carries a suite of instruments that see our world not as our eyes do, but through the analytical lens of multiple wavelengths. Its MODIS instrument, the Moderate Resolution Imaging Spectroradiometer, is a workhorse that scans the entire planet every 1 to 2 days, capturing data in 36 different spectral bands. Each band is tuned to reveal something specific. By looking at the ratio of near-infrared light to red light reflected by forests and grasslands, MODIS can calculate the normalized difference vegetation index, a measure of plant health and density. This allows scientists to monitor deforestation in the Amazon, track the progress of agricultural seasons, and even predict potential famines by assessing crop vitality from space. But the applications go far beyond mapping greenery. The same spectroscopic principles allow other instruments to perform chemical detective work on our atmosphere. Sensors can detect the specific spectral signature of carbon dioxide and methane, two potent greenhouse gases. They don't just confirm these gases are present, they can map their sources and sinks, showing plumes of CO2 emanating from power plants or massive releases of methane from thawing permafrost or leaking natural gas infrastructure. This data is invaluable for verifying international climate agreements and pinpointing where action is most urgently needed. Furthermore, by analyzing how light scatters off tiny particles in the air, satellites can track the movement of aerosols, such as dust storms from the Sahara crossing the Atlantic to fertilize the Amazon rainforest, or dangerous pollution from industrial centers spreading across continents, affecting air quality and human health for millions. The cryosphere, Earth's frozen regions, is also under constant surveillance by these spectral watchdogs. The brilliant, reflective surface of ice and snow has a very distinct signature in visible light. Satellites can precisely measure the albedo, or reflectivity, of the polar ice caps. As warming temperatures cause ice to melt and expose darker ocean water or land beneath, the albedo decreases. This means less sunlight is reflected back into space and more is absorbed as heat, which in turn leads to more melting, a dangerous feedback loop that accelerates climate change. By meticulously tracking the subtle changes in the light reflected from these regions over decades, scientists can quantify the alarming rate of ice loss in Greenland and Antarctica, providing irrefutable evidence of a warming planet and critical data for predicting future sea level rise. This incredible ability to take the pulse of our planet from orbit transforms abstract concepts like climate change into concrete, measurable realities. It moves the discussion from debate to data, providing a global perspective that is impossible to achieve with ground-based measurements alone. The tools to do this weren't invented by climate scientists in a vacuum. They are the direct descendants of the spectrographs and photometers developed by astronomers to understand the composition of stars and the atmospheres of exoplanets. The quest to analyze the ancient light from the cosmos has gifted us with the precise methodology needed to decipher the light from our own world, turning satellites into vigilant guardians that continually scan, analyze, and report on the health of our planetary home. This profound interconnectedness shows that exploring the far reaches of the universe is not an escape from Earth's problems. but one of the most powerful tools we have for understanding and protecting it. Yet as we extend our senses further into the cosmos, a new and critical conversation is emerging, one that moves beyond pure discovery to ask a deeper question: how do we explore responsibly? This is the domain of space ethics, a field concerned with the unintended consequences of our cosmic ambitions, ensuring that our quest for knowledge doesn't come at the cost of damaging the very things we seek to understand. It's a recognition that our actions, even those driven by the most noble scientific intentions, can have lasting impacts, and that we have a duty to be not just explorers but stewards of the heavens. One of the most immediate and visible ethical challenges is now literally flashing before our eyes in the night sky: the rapid deployment of vast satellite megaconstellations. Projects like Starlink, which aim to provide global internet coverage by launching tens of thousands of satellites into low Earth orbit, represent a revolutionary step in global connectivity. But for astronomers, they pose an unprecedented threat to ground-based observation. These satellites are highly reflective, and shortly after launch, they form long, bright trains that march across the sky, easily visible to the naked eye and utterly devastating to sensitive telescopes. The problem isn't just the streaks themselves, it's the cumulative effect. Long exposure photographs, which are essential for capturing the faint light from the most distant galaxies, can be completely ruined by a single satellite passing through the frame. As the number of these objects climbs into the hundreds of thousands, the entire sky background will become brighter, effectively washing out the faint, ancient whispers of the universe that astronomers have worked for centuries to detect. This isn't a hypothetical future problem. It's happening right now, forcing observatories to develop complex software to try to algorithmically remove the satellite trails from their data, a process that is imperfect and results in the permanent loss of some scientific information. The ethical dilemma here is a classic conflict of interest: the undoubted benefit of global internet access versus the preservation of our ability to do fundamental science and maintain humanity's cultural connection to an unpolluted starry night. The conversation is pushing companies and astronomers to collaborate on solutions, such as developing darker satellite coatings, adjusting orbital orientations to minimize reflectivity, and creating better sharing of satellite positional data so telescopes can try to avoid them. But it remains a tense and unresolved balance between technological progress and cosmic preservation. The ethical imperative extends far beyond our view from Earth to the environments we are beginning to physically touch. When we send a rover like Perseverance to trundle across the Martian landscape, we are not just exploring a dead rock, we are visiting a potential habitat. One of the most sacred principles in planetary exploration is planetary protection, the practice of preventing biological contamination between worlds. This works in two directions. Forward contamination is the risk that we might accidentally transport hardy Earth microbes to another planet on our spacecraft. If we were to later discover life on Mars, how could we ever be sure it wasn't just the microbes we brought with us? To prevent this, spacecraft destined for potentially habitable zones, like the Martian surface or the subsurface ocean of Jupiter's moon Europa, are assembled in pristine cleanrooms and undergo rigorous sterilization processes to ensure they are as biologically clean as humanly possible before launch. The other side of the coin is back contamination, which, while considered a much lower risk, is taken extremely seriously. This is the hypothetical concern that any extraterrestrial life we might eventually bring back to Earth could pose a biological hazard. NASA and other space agencies have elaborate, multi-layered containment protocols planned for any future sample return missions, treating the celestial material with the same level of caution as the most dangerous pathogens on Earth. These protocols aren't about fear, they are about profound respect. They acknowledge that these other worlds have their own integrity and that we have a responsibility to explore them without carelessly altering or destroying their native environments before we even have a chance to understand them. This leads to the most profound ethical question of all. What happens if we actually find it? The discovery of extraterrestrial life, even in its simplest microbial form, would be the most monumental event in human history, reshaping our understanding of biology, philosophy, and our place in the universe. But how should such a discovery be handled? The scientific community, through organizations like the International Academy of Astronautics, has developed detailed post-detection protocols. These are not binding laws, but carefully considered guidelines that stress verification, transparency, and international cooperation. The idea is to avoid a chaotic, unilateral announcement that could lead to misinformation or panic. Instead, the process would involve multiple independent confirmations of the evidence, notification of international bodies like the United Nations, and a clear, calibrated public communication plan. The deeper ethical questions are even more complex. If we discovered a second, independent genesis of life on Mars, would that planet then deserve special status, perhaps even rights? Would we have a moral obligation to protect it from any future human activity that might threaten it? And if we were to one day intercept a signal from an intelligent technological civilization, the ethical considerations would become infinitely more nuanced. The debate over whether we should even reply a concept known as active SETI or METI is fiercely contentious. Some argue that broadcasting our presence to the galaxy is a hopeful act of cosmic camaraderie. Others, including renowned scientists like the late Stephen Hawking, have warned that it could be incredibly risky, potentially alerting a more advanced and potentially hostile civilization to our existence. These are not questions for science alone. They are questions for all of humanity, requiring input from philosophers, ethicists, policymakers, and the public. They force us to think not just as citizens of a nation, but as a species, considering the long-term consequences of our actions on a galactic stage. By engaging with these ethical challenges now, we are building a framework for thoughtful, sustainable, and respectful exploration, ensuring that our innate curiosity is guided by wisdom and a deep sense of responsibility for the cosmic community we are only just beginning to join. And the best part is, you don't need a doctorate or $1 million observatory to become part of this grand investigation. The tools to connect with the universe's ancient light are more accessible than ever before, many of them right in your pocket or on your computer screen. It starts with simply knowing what you're looking at, and for that, planetarium software is your perfect guide. Free programs like Stellarium or web-based apps like NASA, Eyes on the Solar System, transform your screen into a dynamic, interactive window on the cosmos. You can fast-forward time to see the dance of the planets, rewind to witness historical eclipses, or zoom out to a God's-eye view of our solar system's orbit around the galaxy. These tools demystify the night sky, labeling constellations, tracking the International Space Station as it glides overhead, and revealing the names of those bright points of light that have captivated humans for millennia. It's the first step from casual stargazer to informed observer, allowing you to step outside and instantly recognize the celestial players in the nightly performance. But what if you want to do more than just observe? What if you want to contribute to real, cutting-edge science? This is where the concept of citizen science truly shines, turning your curiosity into genuine data points for professional researchers. Platforms like Zooniverse host a myriad of astronomy projects where anyone can help. You might be tasked with looking at images from powerful telescopes and classifying galaxy shapes, helping to train algorithms, or even making a discovery that a busy astronomer might have missed. The Galaxy Zoo project alone has led to dozens of scientific papers, with contributions from hundreds of thousands of volunteers around the world. Or you might sift through data from the TESS Space Telescope, looking for the telltale dip in a star's brightness that signals a transiting exoplanet. You're not just playing a game, you're examining real data, and your clicks help map the structure of the universe or find new worlds. It's a profoundly empowering feeling, knowing that you are actively participating in the journey of discovery, classifying the very galaxies whose light has been traveling for billions of years just to reach your screen. Of course, there's still immense value in stepping away from the screen and looking up with your own eyes. You don't need to start with a complex telescope. A simple pair of astronomy binoculars can unlock a surprising amount of detail. They will reveal the 4 largest moons of Jupiter as tiny pinpricks of light arranged in a line, just as Galileo saw them with his primitive spyglass centuries ago. They will transform the hazy patch of the Andromeda Galaxy into a distinct, elongated smudge of light, the combined glow of 1 trillion stars, seen as it was 2.5 million years ago. Binoculars bring the craters of the moon into sharp relief and can resolve star clusters into glittering diamond fields. This simple, hands-on observation is a direct physical connection to the cosmos, a way to personally witness the same light that has inspired astronomers throughout history. To deepen that experience, nothing beats connecting with a community of fellow enthusiasts. Local astronomy clubs are treasure troves of knowledge and camaraderie. They host public star parties where members set up their telescopes and invite the public to look through them, often sharing their expertise with infectious passion. These events are a fantastic way to see distant nebulae, planets, and galaxies through a variety of instruments before you decide to invest in your own. Club members can offer invaluable advice on choosing equipment, navigating the night sky, and even processing astrophotography images. This communal aspect of astronomy reminds us that the wonder of the cosmos is a shared human experience, one that connects us across backgrounds and generations, all united by the simple act of looking up. Finally, your smartphone itself can be a powerful tool for engagement. Apps like Skyview or Starwalk use your phone's GPS and gyroscope to create an augmented reality sky map. Simply point your phone at any part of the sky, and the app will overlay the names of stars, planets, and constellations right on your screen. Other apps will send you alerts for upcoming celestial events, a meteor shower peaking tonight, a conjunction of planets at dawn, or the International Space Station making a bright pass overhead. These tools ensure you never miss a moment of cosmic drama, turning your daily routine into an opportunity for spontaneous skyward glances. By blending ancient knowledge with modern technology, these interactive tools dissolve the barrier between the professional and the amateur, inviting everyone to reach out and touch the light from the distant past, becoming an active participant in humanity's oldest and most ongoing story. So as this journey through the cosmos comes to a close, I want to leave you with a single, transformative thought. Every single time you step outside and glance up at the night sky, you are not just looking at a beautiful, static picture. You are participating in an active, ongoing conversation with the universe itself. Every point of light, from the brightest star to the faintest smudge of a distant galaxy, is a messenger. And these are not just any messengers, they are time travelers, each carrying a unique story from the deep past, a story that has been in transit for years, millennia, or even billions of years, all for the sole purpose of reaching your eyes at this very moment. We've traveled together from the fundamental nature of light, understanding its constant speed and its role as a reliable cosmic courier. We've seen how astronomers use the entire electromagnetic spectrum, from radio waves to gamma rays, as a set of master keys to unlock different doors in the cosmic archive. We decoded the profound importance of redshift, which revealed an expanding universe and allows us to measure both the distance and the age of the light we see. We witnessed the cosmic microwave background, the oldest light we can observe, which shows us the infant universe and the seeds of all future structure. We learned how spectroscopy lets us read the chemical fingerprints in starlight, determining what stars and galaxies are made of. We followed the life stories of stars, from their birth in nebulae to their explosive deaths as supernova, which forge the very elements that make up our world and our bodies. We explored how galaxies evolve over time and how their collective light tells the history of cosmic structure. We grappled with the invisible forces of dark matter and dark energy, which we can only detect through their subtle manipulation of light. We saw how brilliant beacons like quasars and the dramatic effects of gravitational lensing act as natural telescopes, magnifying the faintest glimmers from the early universe. And we celebrated the incredible telescopes from Hubble to Webb that serve as our time machines, capturing this ancient light and bringing the universe's history into crystal clarity. But this is more than just a scientific checklist. This is a fundamental shift in perspective. Light is the universe's memory. It is the thread that connects us to everything that has ever happened. The iron in your blood, the calcium in your bones, the very air you breathe, all of it was forged in the hearts of stars that lived and died long before our sun was born. Their stories of creation and destruction were written in the light of their life and their final, brilliant supernova explosions, and that light has been traveling across the galaxy for eons, eventually finding its way into the chemistry of our planet and into you. You are literally made of stardust, and the light that carries that story is still arriving, still telling us where we came from. This connection is both humbling and empowering. It is a reminder that we are a part of this cosmos, not apart from it. We are the universe's way of becoming conscious of itself, of developing the ability to look back at its own history and understand its own narrative. The next time you find yourself under a clear, dark sky, take a moment, let your eyes adjust, find that faint, fuzzy patch that is the Andromeda galaxy. Remember that the photons striking your retina left that galaxy 2.5 million years ago, when humanity's ancestors were first beginning to walk upright. You are seeing it not as it is, but as it was. You are directly interfacing with the past. That is a form of magic that is real, a magic made possible by patience, curiosity, and the unwavering laws of physics. This isn't the end of the journey. It's an invitation for your journey to begin. Your wonder and your questions are the most important tools we have. So keep looking up, keep asking why. The universe has been sending its messages for billions of years, and it's not going to stop now. We've only just